On a clear night, almost everything you see is darkness. One small stretch of that darkness has a name, the Boötes Void, and it is the emptiest place we have ever found. Most of the dark up there is just space between the stars. This one is different. The emptiness runs so deep and so wide that the astronomers who stumbled onto it spent years checking whether it could possibly be real. You've likely heard it called a hole, or a nothing, or something waiting in the black to swallow us. It is none of those, and the truth is far quieter. So ease back now, let the day go, and let your eyes close if they want to. We're heading toward the deepest dark there is. What is really inside the Boötes Void, if the emptiest place we know is not as empty as it looks? If you go looking for a picture of the Boötes Void, you'll almost certainly find the same one. A round patch of black, deep and total, with a scattering of stars caught around its edge, like a drop of ink that fell on the sky and soaked all the way through. It looks exactly like what the name promises, a hole in everything. That picture is real. It just isn't the void. What people are looking at in that famous image is a small, cold cloud called Barnard 68. It sits a few hundred light years from here, close enough in cosmic terms to count as a neighbor, and it is one of the densest little objects anywhere near us. Not empty at all. It's packed with dust and frozen gas, so thickly that the light of the stars directly behind it can't make it through. So the most famous image of the emptiest place we know is actually a portrait of one of the fullest small things a telescope can find. The picture and the place are opposites. The blackness in that cloud comes from something you already understand, from inside your own house. Hold your hand up in front of a lamp, and the wall behind your hand goes dark. Not because the wall vanished, but because your hand is in the way. Barnard 68 is the hand. The grains of dust inside it are each finer than the soot above a candle, but there are so many of them, stacked across such a depth that a ray of light starting on the far side runs into one grain after another until none of it reaches the front. The cloud isn't dark because nothing is there. It's dark because too much is. Before the dust stops light completely, it changes its color. The smallest grains turn aside blue light more than red, so a star seen through a thinner edge of the cloud arrives looking redder than it truly is, the same way the sun goes orange as it sinks through the thick, low air at the end of the day. Astronomers learn to read that reddening like a depth gauge. The further a star behind the cloud is pushed toward red, the more dust must be sitting between it and us. The cloud was hiding its own thickness in the color of the light that managed to struggle through. And the cloud gives the rest of its secret away. Visible light gets stopped cold, but longer waves, the infrared, slip between those same grains far more easily. Turn an infrared camera toward Barnard 68, and the stars that vanished behind it come quietly back, shining right through the cloud as though it were smoked glass instead of a wall. The darkness was never total. It was only darkness for our particular eyes. The fullness in that picture isn't just sitting there either. A cloud this cold and this tightly packed sits on the edge of becoming something. Draw enough gas and dust into a small enough space, let it shed its heat, and gravity slowly begins to win. Clouds like this one are where stars are quietly assembled, falling inward over long stretches of time until their centers grow hot enough to catch light. The blackness in that famous image is closer to a seed than to a grave. It is matter gathering itself toward becoming a star, which is the opposite of nothing in almost every way that matters. Now set all of that beside what the Boötes Void really is. The void doesn't stop light because there's almost nothing inside it to stop anything. If you stood at its near edge and looked across, the far side would be perfectly clear, the way the opposite wall of an empty room is clear. Light from the galaxies beyond it travels straight through and arrives at us with nothing in its path. The void isn't a curtain pulled across the sky. It's closer to an open window with almost no one standing on the other side. So we have two completely different kinds of darkness, and we mix them up almost without noticing. One is the dark of something standing in front of the view. The other is the dark of there being very little to see in the first place. A shadow thrown on a wall and a wide field at midnight are both black, for reasons that have nothing to do with each other. Barnard 68 is the shadow. The Boötes Void is the field. We have made this exact mistake before, long before any photograph existed. In the 1700s, William Herschel swept his telescope across a dark lane in the stars and took it for a real opening, a gap punched clean through the crowd of distant suns as though he were looking out a window onto nothing at all. It was a natural reading. The dark looked like a hole, so he called it one. More than a century later, Edward Barnard studied these same dark patches and showed they were not openings. They were clouds, cold matter standing in front of the starlight. The man who corrected that old mistake is the man this cloud is named for. And here we are, with his name printed on the very object, making the same mistake one more time, pointing at a dense cloud and seeing a void. A void leaves nothing for a camera to catch, so when the mind reaches for an image of emptiness, it grabs the nearest dark thing it can actually see. And the nearest dark thing turns out to be the exact opposite of what it was trying to picture. We can photograph a full thing. We can't photograph an absence. So we hand ourselves a picture of fullness and quietly call it nothing. Look at that inky black globule, and the question that rises is what might be hiding inside it. Look at the void as it actually is, an enormous clear space with its few lights flung impossibly far apart, and the question changes underneath you. It stops being what's in the dark and becomes why is there so little here when nearly everywhere else there is so much? That turns out to be a harder question than it sounds, and it leans on a word we've been leaning on this whole time without ever testing it. We keep calling this place a void, an emptiness, as if saying so settled anything. But light crosses it freely, and a few faint things still drift somewhere inside it. So what does it really mean to call a place empty? The trouble is the word itself. Void asks you to picture perfect emptiness, a place wiped clean down to nothing, the kind of nothing where you could close your hand and feel nothing at all settle around your fingers. And the honest thing to say is that the universe has never once made a place like that. Not the Boötes Void, not the dark between the galaxies, not anywhere we've ever managed to point a telescope. Reach into the emptiest part of that void, scoop up a handful of it, and you'd still be holding something. A few stray atoms of hydrogen, the leftover warmth of the Big Bang drifting through on its way to nowhere in particular. A thin smoke of dark matter you couldn't see or feel but couldn't sweep out either. Far less than you'd find almost anywhere else, sure. But it's never nothing. And here's the part that turns the whole idea sideways. The thing we're comparing the void to, the ordinary universe we think of as full, is already almost empty itself. Think of it like a ladder. The air in the room around you is unbelievably crowded, every tiny pocket of it packed with molecules bumping into each other billions of times a second. pump almost all of that out, down to the best vacuum we can build inside a sealed chamber, and you've taken out nearly everything, and yet what's left would still feel like a crowded city next to the space between galaxies. Step out into that space, already thinner than anything we know how to make, and the void is thinner again. Every rung down the ladder looks like nothing. Not one of them ever quite reaches it. Spread the whole universe out evenly, and a room-sized piece of space might hold a few lonely atoms and no more. The single breath you just took has more in it than you'd sweep out of a stretch of ordinary cosmos far bigger than you can picture. So when we say the void is empty, what we really mean is that it's thinner than thin, a fraction of an amount that was already close to nothing. Empty doesn't mean zero out here. It just means less, measured against a baseline that hardly counted to begin with. Empty is never something a place simply is, all on its own. It's always a comparison, even when we forget to mention the other half of it. A desert is empty next to a city and crowded next to the surface of the moon. When the void gets called empty, we're holding it up against the crowded little neighborhood we happen to live in, and quietly deciding that our neighborhood is the normal one. The void looks like the strange exception only because we're sitting inside the real exception, mistaking it for the rule. To the people who actually map these regions, a void isn't defined by emptiness at all. A patch of space earns the name when its density drops far enough below the cosmic average, when it's holding well under what a normal span would hold. What marks it out isn't the missing matter. It's how far below the line it falls. And the Boötes Void is known for falling a very long way below that line, and for staying down there across a reach of space that's hard to hold in your head. It isn't even dark, really. Not the way a room goes dark when you switch off the lamp. The whole void is soaked in a faint, even glow, the cooled down light left over from the universe's first moments, arriving steadily from every direction. It never drops all the way to the coldest temperature there is. It just hovers a few degrees above it, lit from the inside by an afterglow your eyes were never built to catch. The emptiest place we know is bathed, without a pause, in the oldest light there is. And underneath even that, there's a floor, and the floor still isn't nothing. Picture carrying a sealed box out into the deepest part of the void and emptying it completely. Every atom gone, every speck of dust, every last stray particle, until the space inside is as bare as space can possibly get. It would still hold something. Empty space itself carries a faint energy, a kind of restlessness woven into the vacuum that never switches off, and it seems to be the same quiet pressure slowly stretching the whole universe wider as time goes on. You can take everything out of a place and still not reach nothing, because the stage all that matter was standing on turns out to have a substance of its own. Maybe that's why the word fooled us so easily. Our senses were shaped in the crowded corner, and they never learned the difference between thin and empty, because we've never had to live in the space between them. Everywhere a person has ever stood, the world is full of air, of light, of solid ground underfoot. Almost nothing isn't something we can call up from memory, so the mind just files it under the one word it already owns, which is nothing. The gap between barely there and truly gone is real, and it's enormous, and we walk straight past it without noticing. Once you let go of the idea that the void is a hole, the question underneath it quietly changes shape. A real hole would only need someone to have made it. But a place that's thinly full of everything, just stretched too far apart to add up to much, is a far stranger thing to explain. Nobody cut this region out of the sky. Something drew it thin and left it that way. And if being empty really just means being thinner than our own crowded little corner, then how much of everything out there is empty in exactly the same way? Look up on a dark night, and the universe seems generous with its stars. They're scattered across the whole sky, in every direction, more than you could ever count, and it feels like the natural state of things, light wherever you turn. But that impression is a trick of where you happen to be standing. Step back far enough that whole galaxies shrink to single points, and the universe stops looking full at all. It starts to look like a web. On the largest scale we can map, matter isn't spread out evenly, the way you'd scatter sand across a floor. It's drawn into long, bright threads, filaments of galaxies strung end to end, crossing and joining at brilliant knots where galaxies pile up by the thousands. And between those threads, taking up nearly all the room, are the dark hollows, the voids. The Boötes Void is one of them, the largest and cleanest we've found, but it isn't a strange exception sitting alone in an otherwise crowded cosmos. It's an ordinary feature of a universe that turns out to be mostly hollow. The filaments, the great walls of galaxies, the glowing knots, all the parts that actually hold something, add up to a thin tracery laid over an enormous amount of almost nothing. Measure the universe by sheer volume, by room, and the empty regions win, and it isn't close. The bright structure is the exception. The dark is the rule. We simply happen to live on one of the threads, in a fairly crowded spot, looking out at a sky that seems full because our particular corner of it is. We didn't always know the universe was shaped this way. For a long time, the safe assumption was that galaxies were sprinkled more or less at random through space, a roughly even fog of them in every direction. Then, in the 1980s, two astronomers, Margaret Geller and John Huchra, set out to measure the distances to thousands of galaxies in a single thin slice of sky and plot them on a map. What came back wasn't an even scatter. The galaxies fell along curving lines, wrapped around great empty bubbles, with one chain of them stretched so far across the map that it later earned the name the Great Wall. The first reaction wasn't excitement so much as suspicion, the worry that the pattern was somehow a flaw in how they were looking. It wasn't. The universe really was built like this, and almost no one had expected it. There's a ceiling built into all of this, at least in theory. Zoom in close and the universe is lumpy, all webs and walls and hollows. But zoom out far enough, past a few 100 million light years, and the lumps are supposed to average away until any one enormous box of space looks much like any other, evenly filled. Cosmologists gave that smoothing out scale a quietly grand name, the end of greatness, the point beyond which nothing is supposed to be any bigger. The catch is that we keep finding things that strain against that ceiling, walls and chains of galaxies so long they sit right at the edge of what the rules allow, and a few that seem to overshoot it. Whether those giants are truly single structures or tricks of perspective is still argued over. And the great voids sit at the very same frontier, large enough that their sheer size becomes a question all its own, not just a number to be measured. And because light takes time to cross all that distance, the map of the web is also a map of time. The far filaments we plot are not how they look now, but how they looked when their light first set out, ages before the Earth existed. We never see the cosmic web as it stands at this moment. We see a composite, the near parts nearly current, the far parts buried deep in the past, all stitched into one picture, as though everything in it were happening at once. The structure is real. The single snapshot is an illusion of timing, a portrait assembled from 100 different ages of the same slowly collapsing thing. The shape comes from gravity working patiently on a nearly even start. In the early universe, matter was spread out almost perfectly smoothly, but only almost. A few regions were a shade denser than their surroundings by the faintest of margins. Gravity takes a margin like that and runs with it. The slightly denser places pull in their neighbors, and the pulling happens unevenly, collapsing first into broad flat sheets, then draining along those sheets into filaments, then sliding down the filaments into the dense knots where clusters gather. Matter flows out of the in-between regions and toward the threads, and the in-between regions, left behind, become the voids. The web isn't a pattern laid over the universe like a coat of paint. It's the track matter left as it fell together. And the web we can see is only the part that lights up. Beneath the visible galaxies runs a far larger structure made of dark matter, the unseen stuff that outweighs ordinary matter several times over. The dark matter gathered into this network first, building an invisible scaffold of filaments and knots, and the galaxies formed afterward, settling into the densest points of a skeleton that was already waiting for them. What we admire as the cosmic web is really a sparse decoration of light hung on a frame we cannot see at all, the way dew picks out the threads of a spider's web that were invisible until the morning caught them. The shape has a strange familiarity to it. The branching filaments of the cosmic web resemble several other things almost exactly. The neurons threading through a brain, the roots of a tree working through soil, the channels a river cuts across a delta. That resemblance isn't a hidden message or a sign the universe is somehow alive. It's something quieter and odder than that. Networks built by simple rules, repeated over and over across a vast range of scales, tend to arrive at the same branching geometry, whether the rule is gravity gathering matter, or water finding the lowest path, or a cell reaching toward its neighbors. The largest structure we know of and the one folded inside your own skull rhyme with each other, not because they're related, but because nature keeps reaching for the same few ways of filling space. Which means the night sky you grew up under was never a fair sample of anything. You were raised inside one of the bright, crowded threads, and you learned to treat crowding as normal, to think of stars everywhere as simply the way things are. The truth runs the other way. The ordinary condition of the universe, the state most of it is in, most of the time, is the quiet near emptiness of a void. The Boötes Void isn't the odd one out in all of this. In a way, we are. There's a deeper strangeness folded into the picture too. The voids aren't passive. As matter drains toward the filaments, the emptiness left behind doesn't just sit there being empty. It pushes outward, growing as the universe ages, pressing gently on the walls of galaxies around it, helping to shape the very threads it is defined against. The hollows and the bright structure aren't two separate things, one real and one absent. They're two halves of a single act, matter falling one way while emptiness opens the other, each carving the other into being. So, picture the whole thing now, the way we'd see it from outside if we could. Not a sky sprinkled evenly with light, but a dark, almost endless volume, threaded through with thin glowing filaments and lit at their crossings with great quiet bubbles of near nothing filling the spaces in between. That is closer to the real shape of the universe than anything you can see with your eyes from the ground. And the void we started with is simply one of those bubbles, neither broken nor wrong, just larger and emptier than most. Once you hold that image, a simple question turns out to have no simple answer. If a void is the empty room between the filaments, then where exactly does the room begin? Walk inward from one of those bright walls of galaxies toward the center of a void, and you would never cross a line, never pass through a doorway, never feel the moment you left the crowd and entered the emptiness. So where does a void actually start, if it has no edge to step over? Picture making the trip anyway. You set out from one of those bright walls of galaxies and travel inward toward the heart of the void, watching for the moment you cross over into the empty. You keep watching. The moment never comes. There's no line painted across space, no membrane to push through, no quiet click as you pass from the full world into the hollow one. The galaxies simply grow sparser around you, and sparser still, until at some point you realize you must be deep inside without ever having entered. A void has no edge, the way a room has walls or a lake has a shore. What it has is a slope. Travel from a dense filament out into a void, and the matter around you falls away gradually, smoothly, the way the glow of a city fades as you drive out into open country at night. There's no final street lamp, no official border where town becomes not town. There's only less, and then less, and eventually almost none. The void is the bottom of that slope, not a container you step into. It's tempting to picture these voids as bubbles, but bubbles betray you at the edge. A soap bubble has a skin. Surface tension pulls the film tight and gives the bubble a real surface, a place where inside ends and outside begins. The cosmic voids have nothing like that. Nothing pulls a wall tight around them. There's no force in nature that builds a membrane at the boundary of an empty region, because the boundary isn't a thing at all. It's just the place where the counting changes. These are bubbles without skins, their edges drawn in pencil on our maps rather than found out there in the dark. So when someone hands you the size of the Boötes Void, they're telling you something subtler than it sounds. The number depends on where you decide the void ends. Pick a strict rule. Count only the regions emptier than some sharp cutoff, and the void comes out one size. Loosen the rule, let in the gently thinning fringes, and it grows. Different methods for finding voids run across the very same patch of sky, return different shapes and different borders, all of them defensible, none of them final. The void's true extent isn't hiding from us, waiting to be pinned down. It's partly a decision we make about how empty has to be before we're willing to call it a void at all. The way the edge actually gets drawn makes the strangeness concrete. Astronomers treat the density of the universe like a terrain, with the dense walls as high ground and the void centers as deep basins. To decide where one void ends and the next begins, they trace the ridgelines, the divides where the slope tips from running down into one basin to running down into another. It's the same idea as the line that wanders along a continent deciding which ocean a falling raindrop will reach. The boundary is real enough to draw, but it isn't a wall. It's a watershed, a crest between two ways of flowing downhill, and like any watershed, it's a thing you follow through a continuous landscape, never a barrier you could bump into. Inside, it isn't uniform either. A void is not a perfectly scoured sphere. The thinning deepens toward the center and eases back toward the walls, and scattered through the interior are fainter threads and smaller hollows, the ghosts of a structure that never fully came together. A void is less a clean hole than a landscape of low places, a broad lowland with its own gentle hills and deeper valleys, all of it lying far beneath the level of the crowded world outside. and the shape that terrain gives back is nothing as tidy as a sphere. We say the Boötes Void to make it sound like a single round chamber, but the real form is lumpy and irregular, more like a hollow pressed into a crowd than a ball carved out of stone. Its walls bulge and dent wherever the surrounding filaments happen to run thick or thin. It isn't sitting in an otherwise full universe either. It's wedged among other voids, each pressing against its neighbors, the thin, bright walls between them shared, the way two neighboring fields share a single hedgerow. A void's edge is almost never the boundary between something and nothing. It's the boundary between one emptiness and the next. There's a deeper reason a void resists having an edge. It isn't sealed. The voids connect to one another through low, thin necks, gaps in the walls where the density never climbs very high, so that the emptiness itself forms a branching network running through the whole universe, just as the bright matter does. Map only the hollows and ignore the light, and you'd find them linked into one vast connected system of tunnels and chambers. The universe, at this scale, is built like a sponge, where the solid part and the empty part are both single connected things, threaded all the way through each other. You could, in principle, drift from the middle of the Boötes Void toward another void entirely, slipping through the low places, and never once cross a wall. A void has no edge partly because it was never fully separate from the rest of the dark to begin with. And the boundary, such as it is, isn't even sitting still. It's a place where something is happening. Because a void holds less matter than its surroundings, it has less gravity to slow the general expansion of the universe, so the space inside it stretches a little faster than average. Matter near the rim feels the denser walls pulling from one side and the faster stretching emptiness opening on the other, and across enormous spans of time, it drifts toward the walls. The edge of a void isn't a wall you would hit. It's a slow current, a region where the universe is gently sweeping its last loose matter out toward the bright threads. Even time refuses to draw a clean line here. A clock runs at a rate that depends, ever so slightly, on the gravity around it. Sink deep into a dense cluster of galaxies, down where the pull is strong, and time passes a touch more slowly. Float in the thin middle of a void, where almost nothing is tugging at you, and your clock runs a shade faster than the same clock back in the crowded world. The difference is far too small to feel, far too small to matter to anything alive. But it's real, and it means the void has no sharp edge in time any more than in space. There is only a gradient again, the rate of passing time easing upward as the matter around you fades toward nothing. The mind wants edges. It wants the world sorted into inside and outside, here and there, full and empty, with a clean line drawn between. The universe, at its largest, almost never obliges. Galaxies fade at their rims instead of stopping. The air thins into space with no surface to mark the change. Even the dense knots where clusters gather have no true outer wall. Everywhere you look on the grandest scale, you find slopes and gradients and slow fadings, and almost nowhere a real boundary. The hard edges we picture are mostly conveniences of our own, lines we draw to make a continuous world easier to speak about. The void just makes that habit impossible to ignore, because it is nothing but slope the whole way down. The hole you might have feared, the one that could open beneath you and swallow you whole, was never there to begin with. You can't fall into a void because there's no lip to fall over, no floor that suddenly drops away. If you drifted toward the Boötes Void, you would simply find the stars around you growing rarer and the dark growing wider, so gradually that you could never name the moment the journey changed. Nothing seizes you. Nothing closes behind you. The emptiness just opens, patiently, in every direction, and lets you keep going. Which leaves a real puzzle behind. A void gives off no light of its own. It marks itself with no edge. It hangs no sign in space that says, "Here I am." It is defined entirely by what it lacks. So, how did anyone ever find it, let alone trace its shape across hundreds of millions of light years when there was never anything there to see? You don't find a void by looking at it. There's nothing there to look at. You find it the way you'd find a clearing in a forest at night, not by studying the clearing, but by noticing where the trees stop. The void shows itself only as a shape pressed into everything around it, the silence sitting in the middle of all the noise. So the whole trick of mapping nothing turns out to be mapping everything else, very carefully, and watching for the place where the everything runs out. That's harder than it sounds, because the sky hands you the wrong number of dimensions. Look up, and the stars and galaxies all seem painted on a single dome, near and far flattened together. A bright one beside a faint one with no way to tell which sits closer. A void isn't a dark patch on that dome. It's a hollow carved into the depth, a region that's empty front to back, and depth is the one thing you cannot see by looking. To find the hollow, you first have to give every point of light its true distance, and turn that flat dome into a solid map you could fly through. The distances come out of the color of the light, and out of the fact that the universe is expanding. As space stretches, it stretches the light traveling through it, dragging each wave a little longer, a little redder, the whole way here. The farther a galaxy lies, the longer its light has been on the road, and the more stretched it arrives. Every kind of atom leaves a sharp fingerprint in the light a galaxy gives off, a set of lines at exact colors, and when those lines all show up shifted toward the red by the same amount, that shift becomes a measuring tape. Read the shift, and you read the distance. Do it for 100,000 galaxies, and the flat dome finally opens into depth, with the voids appearing as the rooms where no fingerprints ever came back. You never actually measured the void itself. You measured galaxies, their light, their distances, and the void appeared in the negative space between them, the way a coastline draws itself once you've mapped the land and let the sea take whatever is left. We have never once detected the inside of the Boötes Void directly. We've only ever measured the bright shore around it, and let the emptiness define itself by where that shore gives out. The redshift gives a clean distance only if all of a galaxy's motion comes from the expansion of space. But galaxies also fall, pulled by the gravity of whatever is densest nearby. Around a void, that pull runs outward, toward the heavy walls, so the galaxies on the near side are drifting away from us a little faster than the expansion alone would carry them, and the ones on the far side a little slower. Those extra motions ride along inside the redshift, blended in with the part that marks distance, and they squeeze the void's shape in the map. The thing we're trying to measure is tugging on the very galaxies we're measuring it with. A void doesn't hold still to be charted. It leaves its prints on the ruler. There are other ways to weigh an emptiness, and the cleanest of them uses gravity itself. Mass bends the path of light passing near it, so the crowded parts of the universe act as faint lenses, nudging the images of more distant galaxies out of place. A void, holding less than its share of mass, does the reverse. Light crossing it bends less than it would through average space, and the galaxies seen through a void come out very slightly spread apart, dimmed and pushed outward, as though viewed through a lens ground from too little instead of too much. We can trace the missing mass of a void by the gentle wrongness in the galaxies lying behind it. And the oldest light of all keeps its own quiet record. The afterglow of the Big Bang, that faint, even warmth filling the whole sky, has been crossing voids and walls for nearly the entire age of the universe. When one of those ancient photons drops into a void, it gains a little energy falling in, then has to climb back out the far side. In a still universe, the climb would cost exactly what the fall paid back, and the photon would leave unchanged. But the void is growing the whole time the photon is inside it, its walls stretching outward, so the climb out is up a shallower hill than the fall in. The photon comes away having lost a sliver of energy, arriving a touch colder than it started. Every great void stamps a faint chill onto the ancient light passing through it, and by stacking many of those patches together, we can lift the cold print of emptiness out of the noise. A single void is often too faint to read this way on its own. The bending of light around one emptiness, the chill it leaves on the ancient glow, each can be too slight to pull cleanly out of the noise. So we line up hundreds of voids, center on center, and average them together until the faint shared signal climbs above the random scatter. What comes out is the portrait of an average void, a smooth, round, idealized hollow that matches no single real one, the Boötes Void included. Much of what we know about voids in general, we learned from a composite that exists nowhere in particular, assembled out of many real holes to reveal the shape they hold in common. There's one more way to test whether we're reading the dark correctly, and it doesn't involve a telescope at all. Inside a computer, you can take the early universe as we believe it began, that nearly smooth spread of matter with its faint unevenness, and let simulated gravity run for billions of years, watching the model pull itself into walls and threads and hollows. When you do, voids appear on their own, unbidden, scattered through the artificial cosmos in roughly the sizes and numbers we find in the real maps. We map nothing, in part, by building whole universes from scratch and checking that they grow the same emptiness ours did. That the model keeps producing voids like the ones we charted is another quiet vote that the holes in our maps are holes in reality and not holes in our method. So we have built an entire craft of cartography devoted to nothing, and it works. The Boötes Void may be the most thoroughly triangulated absence in existence, its shape pinned three separate ways: by the galaxies that ring it, by the mass it fails to gather, by the chill it leaves on the first light. Not one of those methods ever touches the emptiness itself. Each only measures the world bending around the whole. And when three unrelated kinds of evidence sketch the same shape in the same place, the nothing stops being a guess and becomes a known feature of the universe, as solid a fact as any mountain, built entirely out of what isn't there. We are not staring into the dark and inventing what we would like to find there. We are measuring it from three directions with instruments that have no idea how to flatter us, and the dark answers back the same way every time. The emptiest place we know is also among the most carefully measured, and the measurements agree with one another. Even nothing, it turns out, can be known honestly, if you are patient enough to map everything it is not. All of that, though, is the polished work of decades, the method as it stands now, with surveys of millions of galaxies and the theory to read them by. The first time anyone saw the Boötes Void, none of it existed. There were no maps of the cosmic web, no expectation of giant hollows waiting in the data, no plan to go hunting for one. Someone found the largest emptiness we know almost by accident, while reaching for something else entirely. So who were they, and what were they actually trying to do on the night the universe handed them a hole instead? The people who found the Boötes Void weren't hunting for emptiness. They were after a far more ordinary question, the kind that fills most of working astronomy. How are galaxies spread through space? And how bright are they, on average, out there in the dark? In the early 1980s, Robert Kirshner, working with August Oehmler, Paul Schechter, and Stephen Schechtman, set out to measure exactly that, and the emptiness arrived uninvited as a problem in their data. They couldn't map the whole sky. No one could then. Measuring the distance to even a single galaxy meant carefully gathering its light and spreading it into a spectrum, one object at a time, slow and painstaking work. So, instead of surveying a solid block of the universe, they did something more modest and more clever. They chose a few narrow directions, a handful of slim cones reaching out into space, and measured the galaxies that happened to fall inside each one. It was less like drawing a map and more like taking core samples of the cosmos, thin pencils of sky drilled deep in the hope that the samples would speak for the whole. There's a quiet assumption folded into that whole approach. Taking core samples only works if the universe is roughly the same everywhere, so that a few thin pencils can fairly stand in for all the rest. That idea had been the bedrock of cosmology for decades, the principle that on a large enough scale, one patch of space should look like any other. The Boötes Void would become one of the first hard tests of it, a place where the core sample came back so unlike the others that the bedrock itself started to feel less certain. In the cones aimed toward the constellation Boötes, something was wrong. Galaxies showed up close in, and they showed up again far away, but across a vast stretch of distance in between, the samples came back nearly bare. Hundreds of millions of light years of depth with almost nothing in them. Not a thinning, a gap. As though the pencil had passed clean through a hollow in the universe and come out the other side. The natural first thought was that something had gone wrong. A gap that enormous is easier to blame on the method than to believe. Maybe the survey had quietly overlooked the galaxies that should be there. Maybe the instruments had stumbled. Maybe they had simply been unlucky in where they pointed and drilled through some chance lull that meant nothing at all. The history of science is crowded with real discoveries that were first set aside as mistakes because the alternative was too strange to take seriously. An emptiness that size had no business existing. The first thing to rule out was the simplest. Perhaps the galaxies were there and had just been too faint to catch. So they checked what a galaxy of ordinary brightness would have looked like at those distances, and the answer was that plenty of them should have been easily bright enough to see. If the void had been filled at anything like the usual rate, the samples would have been speckled with light. They weren't. The galaxies weren't hiding below the threshold of detection. They were missing. What turned suspicion into a finding wasn't a clearer picture. It was a pattern. The same gap, the same band of absent galaxies at the same distance, kept turning up in separate cones pointed in different directions across that part of the sky. A single empty sample could be bad luck. The same emptiness repeating across independent lines of sight is not luck. It's a shape. Several thin samples, drilled far apart from one another, were all passing through the edges of one single enormous hollow, and only a real structure could leave that mark in all of them at once. The void was confirmed not by seeing it, but by reasoning that nothing else could account for the silence appearing in so many places at the same depth. None of this happened in a single night of revelation. It took further surveys, more cones drilled into the same region over the following years, more long nights of gathering one spectrum at a time before the hollow's true size and shape settled into place. The void wasn't so much discovered as slowly conceded, one stubborn measurement after another, until the universe left no honest way to read the data otherwise. And it arrived at the worst possible moment to be understood. This was before the maps that would reveal the cosmic web, before anyone had watched the universe sort itself into bubbles and walls. There was no picture yet in which a hollow hundreds of millions of light years across made any sense. So the void came in as a pure anomaly, a freak with no frame to sit in, a result that seemed to break the comfortable assumption that galaxies were scattered more or less evenly wherever you looked. Then, over just a few years, the frame caught up with it. The first great redshift maps were drawn, the bubbles and filaments swam into view, and the universe turned out to be riddled with hollows of every size. Almost overnight, the Boötes Void stopped being a freak and became something else, the extreme example of an ordinary thing, the largest and emptiest member of a family no one had known was there. The void itself never changed. What changed was the picture around it, the context that turned an impossible result into a landmark. The pencil beam idea that uncovered the void had a strange afterlife of its own. As astronomers drilled deeper, sampling galaxies along very long, very thin lines of sight, they began to notice that the galaxies didn't fall at random distances. They seemed to clump at oddly regular intervals, wall after wall after wall, spaced almost evenly down the beam, as if the cosmos were layered like rings in a vast tree. Whether that rhythm is a real feature of the universe or a trick of looking through such a narrow window is argued about to this day. But it hinted that voids and walls might alternate across space with something close to a beat, and that the Boötes Void was one deep trough in a far longer wave. And when they looked harder into the hollow itself, it offered up a small surprise. It wasn't perfectly empty. A thin scattering of galaxies turned up inside, faint and far apart, most of them strung along a single delicate thread running through the middle of it. Not a clean hole after all, but a vast near emptiness with a few stubborn lights still burning in it, lights that would go on to raise questions of their own. There's a particular kind of courage buried in this story, and it isn't the dramatic kind. It's the willingness to trust a measurement that insults your expectations. Everything they thought they knew said the gap should not be there. The honest path, and the harder one, was to keep pressing until the data either confessed to a mistake or refused to, and then to believe it when it refused. The largest emptiness in the known universe did not enter science through wonder. It entered as an inconvenience that several careful people declined to explain away. Still, calling it real is one thing. Calling it too empty is another, and that small word, too, is quietly doing a lot of work. A big gap, on its own, proves nothing strange. Space is allowed to be uneven. To say the Boötes Void is really extreme, that it holds far less than it ought to, you first have to know what it ought to have held. So how do you decide how much emptiness is ordinary and how much is simply too much? To call a place too empty, you need a number it failed to reach. Emptiness on its own is just a reading. It turns strange only when you set it against what you expected to find, and the gap between the two grows wide enough to make you stop. So before the Boötes Void can be surprising, there's a quieter question to answer first. How much should have been there? The answer comes from the cosmic average, the typical amount of matter a given volume of the universe tends to hold. Take a region the size of the Boötes Void, anywhere ordinary, and it would be home to thousands of galaxies, the usual crowd of bright spirals and ellipticals scattered through the dark. Look into the void, and you find a few dozen. Not thousands thinned a little. Thousands cut down to a handful, the overwhelming majority of the galaxies you had every reason to expect simply gone. That is the deficit. That is what earns the word to its place. It helps to feel that deficit as distance, not just as a count. In our own crowded neighborhood, galaxies keep close company, near enough that the sky around us stays busy with them. Inside the void, the few that remain are flung so far apart that the gap from one to the next would swallow the distance that holds dozens of galaxies out here. The shortfall isn't only that there are fewer of them. It's that the ones left over have been spread through a room so large that each sits very nearly alone in it. And yet emptiness, by itself, is nothing to be alarmed about. The universe was never smooth. It's lumpy at every scale, dense here and thin there, and small voids are scattered everywhere, the ordinary gaps between ordinary clusters. If every underdense patch were a mystery, the whole sky would be one. So the deficit alone doesn't make the Boötes Void remarkable. Something else does. What matters is how far the deviation runs from the ordinary. Picture all the regions of the universe of a given size, and ask how much matter each one holds. Most cluster close to the average, a little above or a little below, the way most days sit close to ordinary weather. A few run unusually rich, a few unusually poor. The interesting question about any void isn't whether it's empty, but how far out on that spread it sits, how rare a region this drained would be if the universe were simply rolling its everyday dice. A small, shallow void is common, well within the normal scatter. A void this large and this deeply emptied sits far out on the tail, in the territory of the rare. That spread of ordinary deviations isn't arbitrary either. It traces all the way back to the infant universe. When the first light broke free, the cosmos was smoothed to about 1 part in 100,000, almost perfectly even, with only the faintest ripples of denser and thinner running through it. Every structure that exists today grew from those ripples, the richest clusters out of the slightly denser spots, the emptiest voids out of the slightly thinner ones. The lumpiness we measure now is just the grown-up shape of that original near smoothness. So when we ask how rare a void this deep ought to be, we're really asking how deep a dip in that early, gentle unevenness it would have taken to drain a region this far, and the answer places it among the rarer dips of all. Scale is the heart of it. Clearing a small region is easy, cosmically speaking. Gravity only has to nudge matter a short way to leave a little hollow, and the universe is full of little hollows. But emptying a region hundreds of millions of light-years across is a far taller order. Matter has to be moved across enormous distances, and there has been only so much time since the beginning to move it. The bigger the void, the harder it is to dig, and the rarer it should be. A small emptiness is a shrug. An emptiness this size is a question, precisely because it sits at the scale where the ordinary machinery begins to strain. The counting hides a twist too, one that cuts the other way. The deficit looks most dramatic when you count galaxies, but galaxies are not a fair census of matter. They light up only where conditions crowd enough gas together to build stars, which means they favor the dense places and shun the thin ones. A void is emptier in galaxies than it is in raw matter, because galaxies exaggerate every difference, blazing in the crowds and barely catching light in the gaps. So the true shortfall of stuff in the Boötes Void, dark matter and thin gas included, is real but milder than the missing thousands of galaxies first suggest. The void is deeply underfilled. It is just not quite as starved of matter as it is of light. This shifts where the strangeness actually lives. It was never in the emptiness. It's in the distance between the emptiness and what we expected. We aren't unsettled by nothing. We're unsettled by a nothing standing exactly where a great deal of something should have been. A blank wall is unremarkable. A blank wall where you hung a painting yesterday stops you cold. The void disturbs in the second way, not because it is empty, but because it is empty against a background that trained us to expect light. And that background, the thing the void is measured against, isn't a brute fact. It's a prediction. The expected crowd of galaxies comes out of our best model of how structure grows from a nearly smooth start, what should gather, how much, and how fast. So when we say the Boötes Void holds far less than it should, the word should is pointing at the model, not at some certainty carved into the sky. The void is a question aimed back at our own theory, asking whether the rules we trust can really carve a hollow this deep and this wide in the time the universe has had. It sits close to the edge of what those rules comfortably allow, and that edge is exactly where the most interesting questions tend to live. An honest caution has to ride alongside all of this, the kind the demanding part of you is probably already reaching for. Finding one spectacularly empty region and declaring the model broken is a trap. In a universe this enormous, even rare things happen somewhere, and if you go hunting for the single emptiest patch in all the sky, you should expect to turn up something extreme simply because you searched across so much. The real test isn't whether one giant void can exist. It's whether voids this large appear about as often as the rules predict, no more and no fewer. Counted that way, the Boötes Void comes out rare but not forbidden, unusual enough to raise an eyebrow, not quite strange enough to overturn anything on its own. That's the careful position, and it's why the void stands as an open question rather than a settled paradox, a result that keeps the model honest without yet defeating it. We are built to notice deviations, not averages. A room hums along unnoticed until one familiar sound stops, and then the silence becomes the loudest thing in it. We don't register the steady presence of things nearly as sharply as we register the moment something expected fails to arrive. The void is a cosmic version of that missing sound, a deviation so large it rings, an absence held up against an expectation and found short by an enormous margin. The void didn't become unsettling when it became empty. It became unsettling when we noticed the gap between what was there and what should have been. That noticing is the human part, the oldest part, older than astronomy, older than language. So why does the mind seize on a missing thing so much harder than on a present one? And what is it really doing when it feels the weight of something that isn't there? Lie still in a quiet room for a while, and you'll stop hearing it. The faint hum of the house, the distant traffic, the small steady sounds that were there all along. They don't fade because they stopped. They fade because you stopped needing to hear them. And then, if one of them cuts out, the refrigerator settling into silence, a fan clicking off, the absence arrives like a small event, louder in its way than the sound ever was. You notice the leaving far more than you ever noticed the staying. Your senses are built to ignore the constant. A nerve that fires steadily for an unchanging signal soon tires of reporting it, quieting down, letting the brain assume the thing is simply still there. What the brain wants is change, the new, the different, the thing that wasn't true a moment ago. A steady tone sinks into the background within seconds. A break in that tone snaps straight to the front of your attention. We aren't really detectors of the world. We're detectors of difference. If your senses reported everything present, every steady hum and unchanging pressure and constant light, all at once and without pause, you would drown in it, unable to find the one thing that mattered in the flood of things that didn't. Attention is mostly the art of leaving things out. The mind keeps the world usable by ignoring almost all of it, spending its alertness only on the edges where something shifts. To notice the void at all, we had to be the kind of creature that pays attention by subtraction, that finds the signal by knowing what to throw away. It runs deeper than tired nerves. The brain doesn't sit and wait for the world to arrive. It guesses ahead, constantly, building a running model of what should happen next and checking it against what comes in. Most of what you feel you perceive is actually that model, your own prediction of the room, confirmed and left alone. The senses mostly report the mismatches, the places where the world disagreed with the guess. You live, in large part, inside your own expectation of things, and you truly see the world only where it surprises you. Which leads to something strange about how we're wired. Play a steady rhythm to someone, a beat repeating evenly, then drop a single beat. Leave one silence where the next should fall, and the brain answers. A measurable pulse fires at the exact instant of the missing beat, a response not to a sound but to its absence. The expected note that never played leaves a real mark in the nervous system. There is, in the most literal sense, a signal inside you for the sound that isn't there. And the same brain that flags what's missing will also invent what's gone. There's a blind spot in each of your eyes, a place where the nerve leaves and no light is caught at all, and you never see the whole, because the brain quietly paints over it with whatever it expects should be there. People who lose a limb often go on feeling it for years, a hand that itches, fingers that clench, a presence vivid and complete where there is nothing left to sense. The mind both raises an alarm at absence and papers it over with invention, and which one it does depends on what it was expecting in the first place. We are not passive witnesses to what is and isn't there. We are always, in part, supplying the answer. This is the same move that found the Boötes Void. No one saw the emptiness. They predicted a crowd of galaxies, the steady beat of structure that fills most of the sky, and then a long stretch came back silent, and the silence rang against the expectation. The science of mapping nothing and the small jolt you feel when a familiar hum cuts out are the same act, performed at wildly different sizes. A model of what should be there, a gap where it wasn't, and the gap lighting up precisely because something was meant to fill it. We are absence detectors, and the void is the largest missing beat we have ever caught. So absence, it turns out, isn't quite a thing that waits out there in the dark to be found. It's a relationship, the distance between what you expected and what arrived. The missing sound doesn't live in the room. It lives in the gap between your prediction and the silence. The void is no different. Its emptiness is real, but the weight of it, the sense that something is wrong, or vast, or lonely, lives in the space between the galaxies we counted and the galaxies we assumed would be there. Strip away the expectation, and what's left is a region that is simply thin. The drama was always partly ours. Artists have always known the other half of this. In music, the silences aren't holes in the sound. They're part of it. A rest, a held breath between two notes, shapes a phrase as surely as the notes do, and a piece with its silences stripped out would collapse into noise. The brain doesn't treat those gaps as nothing. It hears them as structure, as meaning carried by what was withheld. Absence, used well, isn't the failure of presence. It's a thing in its own right, doing its own work, and some part of us has always understood that the spaces are not empty so much as load-bearing. There's an old reason the missing pulls at us so hard. For most of the long history that shaped the human nervous system, an absence was a warning. The night sounds that suddenly stop because something is moving through the grass. The familiar voice that doesn't answer. The footprint with no foot nearby. A creature that learned to feel the weight of what wasn't there, and to feel it fast, lived a little longer than one that only noticed what was. The faint unease the word void stirs in us is borrowing that ancient alarm, an instinct built for a silence that might mean danger, aimed now at a silence that means nothing of the kind. Right now, in whatever quiet you're lying in, that machinery is running. Your brain is filtering the steady sounds down into the background and holding a soft prediction of the room, ready to flare the instant anything changes. The same equipment you'd use to catch a clock going silent is the equipment you're using at this moment to feel the size of an emptiness hundreds of millions of light years away. And here is the gentle part. The alarm is a reflex, not a verdict. The unease lives in the machinery, not in the void. The Boötes Void is not a held breath or a waiting mouth. It's a very large missing sound, and missing sounds, for all the pull they have on us, cannot reach across the dark to touch anyone. The void is not pure silence, though. A few notes still sound inside it. A scattering of galaxies survived in that great absence, faint and far-flung, and once the mind has finished registering everything that isn't there, it turns, almost helplessly, toward the few things that are. Those stubborn lights are not spread at random. So what are they? The handful of galaxies that stayed. And why did the emptying leave them behind? Scatter a handful of sand across a table, and it lands at random. No pattern, just chance deciding where each grain falls. The galaxies inside the Boötes Void did not land like that. The few dozen that survived in all that emptiness aren't sprinkled evenly through it. They line up. Most of them fall along a thin thread that runs roughly through the interior, a faint seam of light strung across the middle of the dark, with the rest gathered into small, loose knots nearby. The survivors have an arrangement, and an arrangement is a clue. If you could pull back and see only those galaxies, ignoring the great emptiness around them, you wouldn't see a random dusting. You'd see something closer to a faint bridge, a slender chain of galaxies tracing a line through a region that is otherwise nearly bare. Here and there along it, 2 or 3 cling together in little groups, the way survivors of anything tend to find each other. The interior of the void isn't a perfectly scoured sphere with a few specks floating loose in it. It has a shape of its own, quiet and thin, but unmistakably there. Even the count of those survivors turned out to be provisional. The galaxies that live in a void run faint, small and dim and easy to overlook, and the first surveys caught only the brightest of them. As instruments improved, and as astronomers learned to listen for the faint radio whisper of neutral hydrogen gas rather than only the glow of stars, more of them turned up, a scattering of small, gas-rich dwarf galaxies the early counts had walked straight past. The void never grew more crowded, but the number of things hiding in it kept creeping upward as we got better at seeing the dim, a reminder that the emptiness we measure is always partly a statement about how hard we have looked. That thread of light is exactly what shouldn't be there if the void had formed the simple way. Picture a single thin spot in the early universe, slowly draining its matter outward toward the walls, evenly, in every direction. What that leaves behind is a smooth hollow, with whatever few stragglers remain pushed toward the edges or left without order. It does not leave a neat line of galaxies running straight through the center. A clean drain doesn't carve a seam down the middle of the thing it empties. A line of galaxies through the interior looks like a relic, the leftover of a wall that used to be there, a remnant of structure the emptying never quite finished erasing. The most natural reading is that the Boötes Void was not carved as one piece. It was assembled, smaller hollows growing side by side and then merging into one, and the thread is the ghost of the walls that once stood between them, the seam where 2 or 3 separate emptinesses fused into a single great one. The galaxies strung along it are the survivors of those vanished partitions, stranded in the middle when the rooms they once divided became one room. Look closer, and the interior keeps this habit at smaller and smaller scales. A great void isn't a single hollow so much as a nest of them, subvoids divided by tenuous subwalls, the same branching pattern that shapes the whole universe repeated faintly inside the emptiness, at lower and lower contrast. The cosmic web doesn't stop at the edge of a void. It carries on inward, ghostlier with every step, a web drawn in fainter and fainter ink, until it sinks below what we can detect. The thread through the middle is just the boldest stroke of a pattern that goes all the way down. The relic walls inside a void tend to line up with the larger web outside it, the same vast pulls that shape the surrounding filaments reaching in to orient the faint structure within. The galaxies on the seam are often strung along the direction the outside universe was leaning all along. The inside of the void remembers the outside, carrying a faint copy of the cosmic web's grain even here, in the one place that seems most cut off from everything. Nothing in the universe, it seems, is ever quite shaped on its own, not even the contents of a whole. There's something almost archival about this. The emptiness, it turns out, keeps records. The way those few galaxies are arranged is a memory of how the void was made, a sentence still legible in a place that has lost almost everything else. It's the way the furniture left in a half-demolished house can tell you where the walls once stood, where a room ended and a hallway began, long after the walls themselves are gone. The survivors of the Boötes Void map an architecture that no longer exists, the vanished structure of how this hollow came together, written in the only ink that didn't drain away. When the smaller voids merged, the matter sitting on the walls between them was caught in the middle, no longer pulled cleanly toward one outer wall or another, but suspended between competing pulls. Some of it drained away in time. Some of it didn't, or hasn't yet. The thread is structure frozen partway through being erased, matter that was on its way out of the picture when the picture changed around it, and so it lingers, a line of galaxies living on borrowed time in the heart of the emptiest place we know. Isolation, inside a void, comes in degrees. The galaxies strung along the thread at least have the thread, a faint line of company, a few neighbors within reach across the dark. But scattered through the deeper interior, off the seam entirely, are the truly solitary ones, galaxies with no thread to belong to, nothing bound to them across distances that dwarf the gaps between galaxies anywhere else. They are among the most isolated large objects we know of, and there's a strange purity to their situation. Whatever became of them happened almost entirely on their own, with no crowd to push them, no collisions to reshape them, nothing to interrupt the slow, private work of being a galaxy. And so the few lights left in the void are not random wreckage. They're a kept thing, the last legible trace of the void's own past, holding a quiet order the emptiness around them lost long ago. A hollow this large has forgotten almost everything it once contained. The thread running through it is what the void still remembers. Even that memory is on its way out. The thread is underdense like everything around it, so it too is slowly draining, its galaxies drifting apart as the void keeps stretching. Given enough time, the seam will fade. The little groups will lose their hold on one another, and the last legible trace of how the void was made will quietly erase itself. The Boötes Void is not only the emptiest place we know. It's a place actively forgetting its own history, smoothing away the evidence of its making, on its slow way to becoming the featureless hollow it was always going to be. Knowing they line up, though, isn't the same as knowing what they are. A galaxy stranded on that thread has spent its whole long life in a place with almost nothing else around it, no crowds to fall into, no neighbors to collide with, nothing to disturb it for billions of years. A life like that leaves marks. So, what kind of galaxy grows up in near total isolation? And what does an empty sky do to the few that have to live beneath it? The galaxies that live in the void are not the grand ones. You won't find many of the giant ellipticals there, those vast, smooth swarms of old red stars that crowd the hearts of rich clusters. What you find instead tends to be small and blue and still busy. Modest spiral disks and little irregular galaxies full of gas, quietly making new stars, looking less like the elder statesman of the cosmos and more like its working youth. A galaxy raised in emptiness grows up differently from one raised in a crowd, and you can read the difference in its color, its shape, and how much life it has left in it. That's because what happens to a galaxy over its long life depends far less on how it was born than on the company it keeps. In the crowded parts of the universe, galaxies live rough. They fall into one another and merge, smashing two spirals into a single shapeless pile that flares into a burst of new stars and then burns through its gas and goes quiet. They plunge through the hot, thin gas that fills a cluster, and the pressure of that passage strips their own gas away, like wind tearing smoke off a chimney. They suffer near miss after near miss, each close pass tugging them further out of shape. The dense universe is a contact sport, and most of its galaxies carry the bruises. In the void, almost none of this can happen. There's no surrounding cluster gas to strip a galaxy bare. There are no close neighbors to collide with, no crowd to fall into, no steady barrage of near misses pulling at the disk. A galaxy out here gets to keep its gas, hold its shape, and go on doing the one slow thing galaxies do when left alone, turning that gas into stars, gently, steadily, for billions of years on end. It isn't starved and it isn't battered. It's simply undisturbed. Hold on to that word, gas, because it's the key to the whole difference. Gas is a galaxy's fuel, the raw material it slowly spins into stars. Crowded galaxies lose theirs, stripped away or burned through or cut off from any fresh supply, and once the fuel is gone, the new stars stop coming and the galaxy slides toward red and quiet. Void galaxies, undisturbed, keep their tanks remarkably full. They tend to be richer in hydrogen, measured against the stars they've already built, than galaxies almost anywhere else, which is another way of saying they've been unhurried, in no rush at all to spend what they have. They've barely begun to burn through their reserves. The emptiness didn't starve them. It left them with their fuel intact, and the whole future still to spend. This isn't a quirk of the Boötes Void. It's a rule that runs across the entire universe, and you can watch it shift as the crowding changes. Pack galaxies tightly, in the heart of a great cluster, and you find mostly old red ellipticals, their star-making finished long ago. Loosen the crowd, out into ordinary regions, and the blue star-forming spirals begin to appear. Go all the way out to the emptiest places, and the galaxies are smaller, bluer, gassier, more alive than almost anywhere else. A galaxy's character tracks the density of its surroundings so faithfully that you could nearly guess where one lives just by looking at what it's made of. What that really says is unsettling in a quiet way. A galaxy's fate is written less by what it is than by where it sits. Two galaxies could begin nearly identical, the same size, the same age, the same starting gas, and if one ends up in a cluster and the other in a void, they will live opposite lives. The cluster galaxy will be hurried into a violent maturity, its gas spent, its star making over, red and finished while the universe is still young. The void galaxy of the very same age will still be slowly building stars, still blue, still unfinished, with a long, quiet future ahead of it. Same age, opposite stage of life. The only real difference is the address. You might expect such extreme isolation to produce something strange, galaxies warped or stunted by living in so much nothing. For the most part, it doesn't. Void galaxies aren't monsters. They're mostly ordinary galaxies, only more so, a little smaller, a little bluer, a little richer in gas. Their disks often unusually smooth and orderly, precisely because nothing has ever come along to knock them askew. Isolation, it turns out, doesn't deform a galaxy. It calms it. The void doesn't breed the bizarre. It breeds the undisturbed. The differences between a void galaxy and one out on the walls are real but modest, a nudge rather than a transformation. What shapes a galaxy most is still its own mass, how much it managed to pull together in the first place. Environment is the second hand on the wheel, not the first. A small galaxy tends to be blue and gassy, whether it lives in a void or a crowd, and the emptiness mostly tilts the odds a little further that way. The honest picture isn't that the void builds a wholly different kind of galaxy. It's that the void leaves a galaxy freer to be the unhurried thing a small galaxy was already inclined to become. And these galaxies aren't refugees that fled the walls and washed up in the emptiness. They're natives of the thin places. They condensed where the matter was already sparse, along the faint seams and subfilaments running through the void, the same thread we traced a little while ago, and they have simply stayed, living out their whole existence in the only home they ever had. They didn't survive a culling. They formed in the quiet and grew up in it, shaped from the very start by having almost nothing nearby. What they are is what a galaxy becomes when the universe leaves it almost entirely to itself. There's a temptation to read decline into all that emptiness, to assume a galaxy alone in the dark must be a poorer, lesser thing than one in the bright crowd. The physics says otherwise. The lonely galaxy is the one still making stars, still holding its gas, still young at heart, while its crowded cousins have long since burned out and gone red. Out here, being left alone hasn't meant being diminished. It has meant being spared, kept gentle and unhurried, going about its work without the violence that wears down everything in the busier parts of the sky. It's a slower way to exist and a longer one. Nothing forces the pace. There are no deadlines pressing in from the neighbors, no collisions to outlast, no sudden upheavals. Just gas turning patiently into starlight, one quiet age after another, in a place with all the time in the universe and almost nothing to interrupt it. That undisturbed calm carries an unexpected consequence, and it points somewhere stranger than gentleness. A galaxy that nothing has touched for billions of years is also a galaxy that has changed very little, that holds on to a way of being the rest of the universe moved past long ago. It hasn't kept up with the times, because nothing out here makes the times. So what does a galaxy preserve, when it has spent the whole age of the universe almost perfectly undisturbed? And what might we learn from the few objects the cosmos simply forgot to touch? The most complete records of the past tend to survive in the places where the least happened to them. A document survives because no one rewrote it. A buried city survives because nothing dug it up. And a galaxy keeps the story of its own making intact only if nothing came along to scramble it. In the crowded universe, almost everything gets scrambled. Out in the void, almost nothing does. Which makes the few galaxies living there something rare, galaxies whose long history is still legible because no one ever wrote over it. In a busy neighborhood, a galaxy's past gets overwritten again and again. Each merger smashes the old structure into a new one, mixing populations of stars that were born ages and worlds apart. Each burst of triggered star-making and each stripping of gas resets the clock, erasing what came before. By the time a galaxy in a rich cluster reaches old age, its history has been edited so many times that the original draft is gone, buried under revisions. The busiest galaxies in the universe are the ones whose pasts are hardest to read. A void galaxy carries a cleaner manuscript. With nothing to merge into it and nothing to tear at it, it has been free to build its stars slowly, in place, across the whole long age of the universe, laying down its history in order, layer by unhurried layer. The structures a crowd would have wrecked are still intact, thin, extended disks, broad reservoirs of cold gas reaching far past the visible edge, smooth, regular rotation undisturbed by any passing tug. Read its starlight carefully, and you can recover the steady, unbroken story of how it grew, a record kept legible by the simple fact that nothing ever interrupted it. The deepest part of that record is written in the elements. A galaxy starts out made almost purely of hydrogen and helium, the light gases left from the Big Bang, with almost none of the heavier elements that stars forge and scatter as they live and die. Every generation of stars enriches the gas a little more, so the longer and harder a galaxy has churned, the heavier its chemistry becomes. Void galaxies, slow and undisturbed and never fed by material falling in from neighbors, have enriched themselves remarkably little. Some of the small ones out in the emptiest regions rank among the most chemically pristine galaxies we know of, their gas still close to the primordial mix, holding onto a composition the rest of the universe left behind long ago. Chemically, they are closer to the beginning than almost anything else still making stars today. This is what makes them precious, beyond their strangeness. They are the closest thing the universe offers to a controlled experiment. Everywhere else, a galaxy's evolution is tangled up with its surroundings, the mergers and the stripping and the crowding all mixed in, impossible to separate from whatever the galaxy would have done on its own. The void subtracts all of that. A void galaxy shows us what a galaxy does when you take the environment away and leave only its own internal physics running, the pure case, the baseline against which every crowded, battered galaxy can finally be measured. To understand what a neighborhood does to a galaxy, you first have to find one that never had a neighborhood. The void provides it. There's a deeper reason to care about that baseline. The early universe, before the great structures had assembled, was a place where galaxies grew gently and slowly, mostly on their own, long before clusters existed to batter them. So the void galaxies aren't only preserving their own pasts. They're carrying the early universe's whole gentle way of making galaxies forward into the present, still running the slow program that everywhere else got cut short by crowding. Watching one is a little like watching how the cosmos assembled galaxies before it learned to do it violently, except that it's happening now, near enough to study in real detail. The word fossil is really pointing at exactly this. A fossil survives not because it's special, but because it was buried quickly and then left alone, sealed away where nothing could disturb it while everything around it decayed and changed. Disturbance is what destroys a record. Stillness is what keeps one. The void buries its galaxies in time rather than sediment, holding them so undisturbed across so many billions of years that their original form survives where almost everywhere else it would have been ground away. But these aren't fossils in the dead sense, not impressions of something that stopped long ago. They're closer to the living fossils of the deep sea, a creature like the coelacanth or the horseshoe crab, an animal carrying an ancient body plan into the present, not because it froze, but because its quiet corner of the world never forced it to change. The void galaxies are still alive, still making stars, still slowly evolving. They've simply kept an old way of being, an unhurried, gas-rich, gentle pattern of growth, long after the crowded universe abandoned it. They aren't relics of the past. They're the past, still going. It would be a mistake to call them untouched, though, in the strict sense. Even a void galaxy has lived billions of years, made generations of stars, enriched its own gas, slowly rearranged itself under its own gravity. Pristine, here, is a relative word, the same way empty was. These are the least altered galaxies we can find, not unaltered ones, the closest survivors to an original state, not the original state itself. The fossil is real, but it's a fossil that kept growing, and reading it means knowing the difference between what the void protected and what time changed anyway. We tend to assume the richest history belongs to the places where the most happened, the crowded centers, the busy hearts of clusters where galaxies collide and merge and blaze. But the most readable history, the clearest memory of how things once were, survives exactly where the least happened, in the still and the overlooked and the left alone. The universe keeps its longest memory not in its grand events, but in its quietest corners, in the galaxies nothing ever bothered to disturb. No upheavals to recover from, no history to be edited or erased, just a long, unbroken continuity, the same slow work carried on without a break since nearly the beginning. Whatever else the void withheld from these galaxies, it gave them that, an existence with nothing scrawled over it, intact the whole way through. All of this describes a kind of galaxy, a category, the general shape of a life lived in emptiness. But there is one in particular that became the face of it, a single galaxy so alone, so far from any companion, that it earned a quiet fame for its solitude. To feel what any of this really means, it helps to stop talking about a class of objects and look at just one. So what does a single galaxy actually look like, out there by itself, with its nearest neighbor an unthinkable distance away across the dark? Out in the Boötes Void, there is a single spiral galaxy that, by every appearance, is unremarkable. A bright core, two arms winding outward, a disk of stars and gas turning slowly the way spirals do, the kind of galaxy you'd pass over without a second look in a crowded patch of sky. It doesn't even have a proper name. It carries only a catalog tag, a short string of letters and numbers, the sort of label we hand to objects no one expected to care about. And yet this ordinary spiral became, for a while, the most famous example of solitude in the entire universe. Look at a sharp image of it, and your first impression is that it has plenty of company. The frame is dusted with other points of light, scattered here and there across the dark. But almost none of them are neighbors. A few are foreground stars, sitting in our own galaxy, far in front of the spiral and nothing to do with it. The rest are background galaxies, lying so much farther away that calling them neighbors would be like calling a city on another continent your next-door house. The picture looks populated. The galaxy at the center of it is alone. What seems like a crowd is only the illusion of a flat image, near and far pressed together, with all the real distance hidden. That this galaxy has only a number for a name is a small accident, but it rhymes with its situation. No one singled it out, because no one expected to. Its anonymity and its isolation match, an object overlooked in our catalogs in much the way it has been overlooked by the rest of the universe, left without neighbors and without a name, known mostly for having so little around it. And the real distance is hard to take in. The nearest galaxy of any real size lies so far from this spiral that the gulf between them would swallow our entire local family of galaxies, dozens of them, several times over, and still leave room to spare. Where we live, galaxies keep close company, near enough to pull on one another, to trade stars, eventually to collide. This one has no such company within reach at all. It has spent its whole existence beyond arm's length of everything, the nearest real light, an immense and unbridgeable distance off across the dark. And there's a second distance folded into the first, one that's easy to forget. We aren't seeing this galaxy as it is. We're seeing the light it sent out hundreds of millions of years ago, long before there was anyone here to look. Whatever it's doing now, in the present we imagine we share with it, we won't learn for hundreds of millions of years more. Even our gaze reaches it only across an unbridgeable gulf of time. The loneliest galaxy is kept at arm's length, not by space alone, but by the slowness of light itself, met always a little too late ever to quite be known. None of that has stopped it from being a perfectly working galaxy. Its arms are still well formed, its disk still turning, its gas still condensing quietly into new stars. Set it down in a crowded part of the sky, and you would not be able to tell from the galaxy itself that it had spent billions of years in near total isolation. It is like a lighthouse that has gone on turning its beam, faithfully, night after night, across a sea where no ship has passed in living memory. The light doesn't dim for lack of an audience. The galaxy doesn't falter for lack of neighbors. It simply carries on, complete in itself, doing everything a galaxy does with no one and nothing nearby to do it for. Its spiral arms are symmetric, its disk smooth, with none of the torn streamers or warped edges that give away a galaxy that has been in a fight. Bright knots of blue mark where new stars are still forming along the arms. Everything about its appearance says undisturbed, a galaxy that has never been pulled out of true by a passing neighbor, because it has never had one close enough to do the pulling. The portrait of the loneliest galaxy turns out to be, fittingly, a portrait of the calmest. How a galaxy ends up this alone is its own small puzzle. Most likely it simply formed where it is, condensing out of one of the thin seams running through the void, never having neighbors to begin with. But there's another possibility that lingers in cases like this, and it's a strange one. Some deeply isolated galaxies carry faint scars, gentle ripples and shells in their outer light, the kind left behind when a galaxy has swallowed a smaller companion in the distant past. It raises the quiet possibility that the loneliest galaxies might, in some cases, have made themselves lonely, absorbing the few neighbors they once had until none were left. Whether that's the story here or not, the thought stays with you, that some solitude is there from the start, and some is the slow result of having outlasted everything close. Lonely is ours, not the galaxy's. A spiral has no awareness to feel its isolation, no sense of the empty distances around it, no wish for company it cannot have. It lacks nothing. It wants nothing. It spins on exactly as it would in the thickest crowd, indifferent to a solitude that exists, as a feeling only in us. We look at a single light in all that dark, and something in us aches a little on its behalf, and that ache is real, but it belongs to the watcher, not the watched. The galaxy is not lonely. It is simply far from others, which is not the same thing at all. One galaxy moves us more than the whole vast statistic of the void ever could. The emptiness, described in distances and densities, stays abstract, too large to feel. But one spiral, turning alone in the dark, is something the mind can actually hold. It makes the scale land. And the speed with which we reach for the word lonely, the way the image tugs at us almost before a thought can form, says less about the galaxy than about us, about how deeply we are built to notice when something is by itself, and how readily we hand our own feelings to anything we find out there alone. So here it is. A faint spiral, its arms wound loosely around a quiet core, turning in a darkness that runs unbroken for distances the mind cannot hold. No nearby star to rise or set in its sky. No companion to pull at its edges. Only the slow, patient turning, the same as it has been for billions of years, in a silence that nothing has ever arrived to break. The galaxy works. It functions completely, lacks nothing, carries on. But it does all of it in a solitude so deep that even time out there must pass strangely, with nothing to mark its passing, nothing to interrupt it or hurry it along, no events at all but its own slow turning. What is time like for something that alone, and does isolation this complete change the very rhythm of a galaxy's long life? Time, in the strict sense, barely runs differently out there. A clock in the empty heart of a void ticks just a shade faster than one down in a crowded cluster, but the difference is so small it would take the whole age of the universe to add up to anything you'd notice. That isn't where the strangeness lives. The strangeness is that, for a galaxy this alone, almost nothing ever happens. Its clock runs fine. Its calendar is nearly blank. Think about what fills the long life of a galaxy in a busy part of the sky. Collisions, mergers, the sudden flare of star-making when two disks slam together, near misses that wrench it out of shape, the slow theft of its gas as it plows through the hot medium of a cluster. A crowded galaxy's history is a string of events, one upheaval after another, each of them a marker, a before and an after. The Void Galaxy has none of these. Nothing arrives. Nothing collides. Nothing interrupts. Its whole existence is a single smooth stretch with no markers in it at all, just the same slow turning and the same slow making of stars, carried on without a break since nearly the beginning. It's the difference between two rivers. One runs through broken country, full of falls and rapids and sudden forks, its water thrown into white chaos at every turn, its course a series of events. The other crosses a wide, flat plain, and with nothing in its way, it runs slow and straight and almost silent, hardly seeming to move at all, though it covers just as much ground in the end. The galaxies of the crowded universe are the mountain rivers, all turbulence and incident. The Void Galaxy is the river on the plain. The water is the same. What changed is the land it had to cross, and the void is the flattest, emptiest country there is. Our own galaxy, for what it's worth, is one of the mountain rivers. The Milky Way has a collision in its future, a slow, grand merger with the great spiral of Andromeda, already falling toward us, due to arrive in a few billion years and rearrange both galaxies completely. We live on a turbulent stretch, with an event the size of a galaxy bearing down on us, unhurried but certain. The Void Galaxy faces nothing of the kind. No Andromeda slides toward it. No merger waits in its future, no upheaval, no rearrangement, ever. Where our sky holds an approaching collision, its sky holds only more of the same quiet it has always known. There's something here we know from the inside, even if a galaxy can't. We measure time by what happens in it. A day crowded with events feels full, and afterward it feels long, because memory has so much to hang on. A stretch where nothing happens slips past almost without a trace, the days folding into one another, a week gone before you've marked its passing. Change is what gives time its texture. Strip the change away and time doesn't stop, but it loosens, smooths, loses its edges. The Void Galaxy lives at the far end of that, an existence of almost perfectly unmarked time, where one age is much like the next and nothing ever divides the long, smooth flow into a before and an after. With nothing outside to mark its time, such a galaxy becomes its own only clock. The single thing changing in its world is itself, the slow wheel of its rotation, the gradual graying of its oldest stars, the unhurried birth of new ones. Out here there is no other timekeeper, no passing event to measure the years against, only the galaxy's own quiet aging telling it, if anything could tell it, that time is moving at all. It is both the thing that changes and the only record of the change. And the slowness buys something the fast galaxies never get. A galaxy that spends its gas in a single violent burst, burns bright and then goes dark, finished young, red and quiet while the universe is still in its youth. The Void Galaxy, sipping at its fuel, making a few stars at a time across uncounted ages, is still going long after its hurried cousins have died. Slowness is a kind of longevity. The undisturbed galaxies, the ones nothing ever happened to, will be among the last still making new stars when most of the bright, crowded places have long since burned out. In the long run, the quiet ones outlast the loud. That puts them at the gentle end of the universe's future. The most eventful things change the fastest and end the soonest. The least eventful endure. A void galaxy, with almost nothing able to reach it and almost nothing left to disturb its slow routine, is about as close as the cosmos comes to a thing that simply persists, changing so little, so slowly, that it will still be recognizably itself when far grander structures have come apart. The emptiest place protects the most lasting lives. It's no small thing, that kind of stillness. People go to real lengths to find a faint version of it, a quiet room, a long walk, the few unhurried minutes before sleep, some stretch of time with nothing in it that has to be answered. We reach for the eventless on purpose, in small doses, because the constant arrival of things wears on us. The void galaxy has by accident, and in full, the very stillness we keep trying to borrow. In the quiet you're lying in right now, time is doing a little of the same thing. With the day's events behind you and nothing new arriving, the markers fall away, and the minutes begin to lose their hard edges, running together the way they do just before sleep. It's a small, ordinary taste of unpunctuated time. The kind of slow, eventless flow that, stretched across billions of years and emptied of everything, is the whole existence of a galaxy alone in the void. Nothing pressing, nothing to react to. Only the slow, continuous unfolding of a thing left entirely to itself. We've followed what the void shelters and how unhurried its few lives are, the slowness it grants, and the long endurance that comes with it. But we still haven't asked the question sitting underneath all of it. This enormous hollow that holds such quiet, unpunctuated existence, where did it come from? And how do you carve a piece of nothing that large out of a universe that began nearly the same everywhere? The honest answer to where the void came from is that no one carved it, and nothing punched it, and it was never quite full to begin with. The Boötes Void did not start as a crowded region that something later emptied out. It started as a region that was, from the very first moment, a little thinner than everywhere else. The hollow we see now isn't a hole cut into a solid universe. It's the grown-up shape of a faint head start in emptiness, present from the beginning, before there were stars or galaxies or anything at all to empty. To find the seed, you have to go back to when the universe was almost perfectly smooth. In its first moments, matter and energy were spread out so evenly that the differences from place to place were almost too small to picture, a region heavier or lighter than its neighbors by no more than 100,000th, a whisper of unevenness laid over a near-perfect calm. Those whispers were the seeds of everything. The slightly heavier spots would, in time, grow into clusters and walls and galaxies. The slightly lighter spots would grow into voids. And one of the lighter spots, a faint shortfall in the smoothness, was the beginning of the Boötes Void. Those original ripples came from somewhere stranger than you might guess. The leading account traces them to quantum fluctuations, the tiny, unavoidable jitter that haunts even empty space at the smallest scales, the same restlessness we met earlier in the vacuum. In the universe's first sliver of a second, space is thought to have stretched at a staggering rate, and that violent expansion seized those microscopic quantum jitters and blew them up to enormous size, freezing them into the fabric of the cosmos as faint patterns of denser and thinner. The blueprint for every galaxy and every void was, on this account, quantum static, magnified beyond all recognition, and printed across the sky. There's an inversion buried in that, worth holding on to. The largest things in the universe, the great walls and the vast voids, grew from the smallest things there are, the quantum tremor at scales far below an atom. The Boötes Void, one of the biggest single structures we have ever mapped, is in the end a magnified piece of quantum static, a flicker of subatomic uncertainty caught by the expansion of space and stretched until it spanned a third of the way across everything we can see. The very large and the very small turn out to be the same story, told at opposite ends of an almost unimaginable zoom. And we can very nearly see it. The oldest light in the universe, that faint, even glow we keep returning to, carries a map of those original ripples, printed across the whole sky as a pattern of very slightly warmer and very slightly cooler patches. The warmer patches mark where matter was a touch denser, the cradles of the future clusters. The cooler patches mark where it was a touch thinner, the cradles of the future voids. Somewhere in that baby portrait of the universe, in principle, is a faint, cool smudge that was the infant Boötes Void, a slightly emptier ripple that had not yet begun to grow. What we see and what we infer are worth keeping apart here. The seeds themselves are not a guess. The pattern of warmer and cooler patches in that ancient light is measured, mapped in fine detail, as solid as any photograph. What remains the leading idea, rather than settled fact, is the deeper story of where the seeds came from, the account of quantum jitter stretched by a burst of early expansion. The ripples are observed. Their origin is our best reconstruction, held with confidence but not with certainty. The void's birth is real. The exact story of how it was conceived is still, in places, being written. Those seeds weren't pure random noise either. In the hot, dense first age of the universe, before atoms formed, matter and light were locked together into a single glowing fluid, and that fluid rang. Pressure waves, real sound, rolled through it, and when the universe cooled enough to let the light go free, those waves froze into the pattern of the seeds, leaving a faint preferred distance built into how matter and emptiness would later arrange themselves. A ghost of that early ringing still lingers in the spacing of galaxies and voids today, a built-in scale, the sound of the infant universe printed into where its great structures would one day stand. The voids were shaped, in part, by music that fell silent long before there was anything to hear it. The overdense seeds and the underdense seeds began as mirror images of each other, equal and opposite deviations from the same smooth average, two sides of a single field of ripples. The cluster and the void are twins, born from the same faint unevenness, one a little above the line and one a little below. We tend to think of galaxies as the real things and voids as their absence, the leftover gaps. But at the beginning they were equals, the same kind of ripple with opposite sign, and the void has just as old and just as honest a birth certificate as any galaxy that ever formed. And the same field of ripples that dipped to make the void rose elsewhere to make us. The overdense spot that became our own galaxy, the matter that gathered into the sun and the earth, the atoms now reading these patterns back, all of it grew from a slightly heavier ripple in the very same primordial static that, a little to one side, sank low and became the great emptiness. We and the void were drawn from the same deck, opposite cards off the same shuffle. The thing we find loneliest in the universe and the warm, crowded corner we came from are siblings, set apart only by the sign of a fluctuation no larger than 100,000th, an unthinkably long time ago. This changes what the word empty means yet again. The void isn't space that lost its matter. It's space that started with slightly less and was always going to end with far less, its future thinness already implied in that first faint shortfall. Emptiness wasn't done to it. Emptiness was its inheritance, written into the seed, waiting only for time and gravity to draw it out. The Boötes Void has been becoming empty since the universe was a fraction of a second old, following a path set before the first atom existed. The location of the largest emptiness we know was decided absurdly early, and by nothing that meant to decide it. No force chose to open a hollow there. A pattern of essentially random quantum ripples settled in the universe's first instant, happened to leave that particular region a hair below average, and from that accident, billions of years before any eye existed to find it, the place of the Great Void was already fixed. The map of where the cosmos would be full and where it would be empty was sketched, in faint quantum pencil, before the universe was old enough to have made a single star. A faint head start, though, is all the seed really is. A region 100,000 thinner than its surroundings is still, at that point, almost exactly as full as everywhere else. Left alone, such a whisper of a difference would do nothing at all. The seed explains where the void would grow, and that it would grow, but not how a shortfall that slight could ever become the emptiest place in the universe. Something had to take that almost nothing of a head start and run with it, hard, for billions of years. And that is the part that turns a faint ripple into a vast silence. Gravity does not treat a thin region and a thick one evenly. It plays favorites, and it plays them relentlessly, in a way that takes the slightest difference and widens it without end. So how does a whisper of emptiness, a region barely below average at the dawn of everything, grow into a hollow hundreds of millions of light years wide, with almost nothing left inside it at all? Gravity is not fair, and the void is what its unfairness builds. The rule that runs the whole thing is almost cruelly simple. A place with a little more matter has a little more gravity, and a little more gravity lets it gather still more matter. A place with a little less has less pull, and less pull means it can't hold on to what it has when something richer nearby begins to take it. More begets more. Less begets less. From a beginning that was nearly even everywhere, that one rule, applied without rest for billions of years, sorts the universe into the crowded and the empty, and drives the difference toward the extreme. Watch it play out on the dense side first. A region that starts a hair above average pulls its surroundings inward a little more strongly than its neighbors do. The matter it draws in raises its density, which strengthens its pull, which draws in more, which raises its density again. It compounds, the way a small lead in money compounds when the returns are reinvested, each gain making the next gain easier, the advantage widening on its own. In gravity, as in wealth, the early head start doesn't simply persist. It grows, faster and faster, into dominance. The void is the same story run in reverse, and it's the harder one to picture because nothing is being added anywhere. A region that starts a hair below average has slightly weaker gravity than the denser places around it. So when the long tug-of-war for matter begins, it loses. Its matter is drawn outward, toward the richer regions that pull harder, and every bit it gives up leaves it thinner still, with even less gravity to hold the rest. Thinner means weaker, weaker means it loses more, and losing more means thinner again. The void doesn't get emptied by some force reaching in. It empties itself by being too poor in matter to keep the little it has. Think of the matter in the early universe as resting on a gently uneven landscape, where the dense regions are valleys and the thin regions are low hills rising between them. Matter rolls downhill, off the hills and into the valleys, and a void is one of those hills, a rise that everything slowly slides away from. Stand at the center of a forming void, and the matter around you isn't holding still. It's drifting outward in every direction, off the rise, down toward the surrounding walls where the valleys are deepening. The emptiness at the center isn't where matter was removed. It's where matter was always rolling away from. And this outflow isn't only a story we tell with equations. We can measure it. The galaxies near a void's edge carry a faint extra motion in their light, a slight drift outward, away from the center, laid on top of the general expansion, exactly the signature you'd expect if matter is being shed from the hollow toward the walls. The runaway leaves fingerprints, and they show up in the real sky. The void is caught in the act of emptying itself, the outflow still going on, still measurable today. A second push works alongside the first. The whole universe is expanding, with the gravity of its matter acting as a brake, slowing the stretch. Inside a void, with less matter, that brake is weaker, so the space itself expands a little faster than the average everywhere else. The void thins in two ways at once then. Its matter drains outward toward the walls, and the space left behind stretches faster than the rest of the cosmos, pulling apart what little remains. Less matter staying, and more room opening between whatever does. Both effects feed the same growing emptiness. But the two sides of the story, the filling and the emptying, are not perfect mirrors, and the difference shapes everything. An overdense region has no limit to how dense it can become. It can collapse and collapse, its matter piling up without any ceiling, until it forms the tight, violent knots where clusters and galaxies live. A void has a floor it cannot pass. It can approach empty, but it can never go below empty, never reach less than nothing. So the dense regions run away toward extremes, collapsing into small, sharp, crowded structures, while the voids can only spread, gently and without violence, toward a thinness that has nowhere lower to fall. The crowded universe is compact and harsh because density has no ceiling. The empty universe is vast and calm because emptiness has a floor. That gentle spreading does something to a void's shape over time. As matter flows evenly outward in every direction, it tends to round the hollow out, smoothing it toward a sphere, the way slowly escaping air rounds a bubble. Meanwhile, the matter collecting on the outside sharpens into thinner and thinner walls and threads. Emptiness, left to itself, rounds. Matter, drawn together, sharpens. The smooth bubbles and the sharp web are the two natural endpoints of the same unfair rule. The rounded hollows where matter rolled away and the sharpened seams where it piled up. Step back, and what gravity really is, on these scales, is an engine of inequality. Hand it a universe that begins almost perfectly even, with differences no greater than 100,000th, and it will spend billions of years patiently widening those differences into the starkest divide in nature, the gulf between the dense and the empty, the crowded clusters and the vast hollows. Nothing intends it. No unfairness of motive sits anywhere in it. It's only what happens when a force that always pulls is let loose on a field that started the tiniest bit uneven. The Boötes Void is the deepest have, not the universe ever produced, and it became one by the most ordinary rule there is, that to have less is, in the end, to lose more. The widening wasn't steady through all of cosmic history either. For a long stretch, while the contrast was still small, the runaway barely got going, the growth creeping along almost in proportion, the void deepening at a crawl. Only as the difference built did the process gather pace, the emptying speeding up as the void grew emptier and the walls grew heavier, the feedback tightening on itself. The most dramatic draining is a relatively late chapter, not an early one. The void spent much of its existence as a modest dip and did the boldest part of its emptying in the universe's later ages, which makes the question of timing sharper than it first appears. None of it ever happened quickly, though. This is a runaway, but a slow one, the contrast widening by tiny degrees across stretches of time too long to feel. No single moment in it would have looked dramatic, the matter sliding off the rise so gradually that nothing about the void at any given age would have seemed like an event. The emptiness we see now is the sum of an unhurried draining, carried on without pause and without haste, since close to the beginning of time. And that slowness raises a real problem, one that has nagged at the people who study these hollows for decades. The runaway is relentless, but it is gentle, and gentle things take time. Gravity works softly on scales this large, widening a void only so fast. So a hard question waits underneath the whole tidy story. Has there even been enough time, in the entire age of the universe, for so slow a process to open a hollow this enormous? Or is the Boötes Void, in the end, simply too big for the clock that was supposed to have made it? Run the slow runaway forward for the ordinary hollows, the small and middling ones, and the timing works fine. Run it for the biggest, deepest voids, the Boötes Void among them, and the clock starts to come up short. Take a single faint seed, a region 100,000th below average, and let gravity drain it the patient way we described, and there may simply not have been enough time, in the whole history of the universe, to open a hollow this enormous and this empty. Part of the trouble is that the clock is shorter than it looks. Gravity hasn't had the universe's entire life to build structure. In the first stretch after the beginning, the cosmos was ruled by radiation, and that fierce early environment held the growth of structure back, barely letting the seeds deepen at all. Much later, a different influence took over and began shutting structure building down again. The real window in which gravity could freely sculpt the matter, deepening the voids and raising the walls, was a limited middle stretch of cosmic history, not the full run of it. The time available to dig the great hollows was less than the age of the universe, and the largest of them needed every bit of it, and perhaps more. That late shutdown bites harder than it first seems. The thing that began closing the window was the acceleration of the universe's expansion, an influence we'll come to properly soon. Once the expansion started speeding up, it began pulling regions apart faster than gravity could gather them, and the slow building of structure stalled out, the voids and walls roughly freezing at the contrast they had reached. The hard part is the overlap. The great voids were doing the boldest stretch of their deepening in the universe's later ages, exactly when the accelerating expansion was starting to slam the door on any further growth. The largest hollows needed more time, right as the universe was taking time away. And what that window had to accomplish was steep. A seed begins as the faintest imaginable dip, a difference of 100,000th. To become a true void, that dip has to deepen enormously, the contrast between the hollow and its surroundings growing by a huge factor before the region counts as anything like empty. For a modest void, the slow runaway manages it with time to spare. For one, the size of the Boötes Void, draining a region hundreds of millions of light-years across down to a fraction of the normal density, the same slow process is asked to do far more across a far larger region in the same limited time. It's like being told to empty a small pond and a vast lake with the same trickle in the same afternoon. The pond is easy. The lake is another matter. The budget is tighter than it sounds. Across the whole window, when gravity could work, it could only deepen the original ripples by so much, magnifying that faint starting contrast by something like a few tens of times before the growth stalled. For most structures, that's plenty. But the deepest, widest voids need nearly the whole of that budget spent on them, and a little more besides. They sit right up against the ceiling of how much a single seed could have grown in the time the universe has been running. There isn't margin to spare, and for the very largest, there may not be margin at all. It's important to be exact about what this does and doesn't mean, because it would be easy to oversell it. The puzzle is not that the void is impossible, or that the laws of gravity fail, or that our picture of the universe is broken. Most voids fit the timing comfortably, with room left over. It's only at the extreme, the very biggest and emptiest hollows, that the simplest account begins to strain. And the strain isn't in the physics. It's in an assumption we slipped in without noticing, the assumption that a void this large grew, cleanly, as a single hollow, out of a single seed. That one quiet assumption is what the clock can't quite afford. The Boötes Void sits right at that edge, close enough to the limit the easy story runs short, far enough out that it demands a better one. Results like this are not failures. They're where a theory gets tested for real, at the extreme case that won't quite fit the first, simplest telling, the place where you find out whether your assumptions were the truth or only the convenient version of it. There's a spectrum to these puzzles, and the void's time problem sits at the gentle end of it. It's the milder, more resolvable kind of tension. There are stranger ones still argued over. The giant walls and chains of galaxies that brush against the end of greatness. Structures that seem, to some, too large for the universe to have any business making at all. Next to those, the Boötes Void is a soft puzzle, the sort that bends the simplest story without threatening the whole framework. Knowing which puzzles are which, the cracks that close with a better account and the cracks that might run deeper, is most of what keeping an honest theory actually means. We had it so cleanly. A faint seed, a relentless runaway, emptiness drawn out of almost nothing by the most ordinary rule there is. And it's true, all of it. It just isn't the whole truth for the largest case, and the gap between the clean story and the stubborn size of the real thing is exactly the kind of gap that good science is meant to feel rather than smooth away. The void, once again, keeps the theory honest by being the one case that refuses to fit the simplest account of how it was made. A reassurance hides inside the difficulty, though. When we build whole model universes in a computer, with the real cosmology and the full tangle of gravity running freely, large voids do appear, hollows as big as the great ones we map, formed without breaking a single rule. Which tells us the trouble was never with the physics. It was with the hand-drawn version of the story, the lone seed quietly emptying one region in a straight line. The full reality is messier and more generous than that simple sketch, and somewhere in the mess is the room the clock seemed to deny. The simulations make these voids. The simple story just couldn't, on its own, explain how. So the way through isn't to break anything. It's to drop the one assumption that was costing all the time, the idea that the void had to be dug whole, in one place, out of one seed. Loosen that, and the clock stops being a problem. Because there's another way to arrive at a hollow this enormous, one that asks no single region to do the impossible, and the universe left us a clue to it long ago, sitting in plain sight in the very middle of the void. We've already seen the clue, in fact, and passed right over it. The thread of galaxies running through the void's heart, the faint seam we found earlier and read as a relic, a leftover wall. A wall between what? Between rooms that used to be separate. What if the Boötes Void was never one hollow that gravity had to empty all at once, but several smaller hollows, each one modest enough to form easily within the time allowed, that grew up side by side and then merged into a single great emptiness? Could the largest void we know be less a thing that was dug, and more a thing that was assembled? The answer is yes, most likely, and it dissolves the whole problem at once. The Boötes Void was probably never dug as a single hollow. It is, in all likelihood, the union of several smaller voids, each one modest enough to have formed easily in the time available, that grew up beside one another and then ran together into a single great emptiness. The size we marvel at isn't the achievement of one region draining against the clock. It's the sum of several ordinary drainings added together by merging. No single seed had to do the impossible. The impossible was shared out among many that each did only the possible. That's the move that buys back all the missing time. The slow runaway can't take one seed and empty a region this vast within the age of the universe. But it doesn't have to. Small and middling voids form readily, well inside the budget, scattered everywhere through the cosmic web. Let a cluster of them happen to grow side by side, each draining its own modest region at the ordinary pace, and their hollows widen until they touch. When they join, their volumes simply add. You reach an enormous emptiness not by growing one contrast to monstrous depth, but by combining many achievable ones into a single connected space. Size by union, not size by overreach. The merging itself is gentle, and it leaves a mark. Picture a worn cloth with several small holes opening in it. As each hole widens, the fabric between them thins, the threads pulling apart from both sides at once, until at last the holes connect into one larger tear. And the very last threads to give way, the strands that bridge two holes the longest, hang on in the middle of the new opening, even after the rest is gone. That's close to what happens to the walls between merging voids. The matter on a wall is drained from both sides, the wall thins, and eventually the voids open into each other, but the last, densest strand of the old wall lingers across the middle, not yet fully drawn away. And that lingering strand is something we've already met. The thread of galaxies running through the heart of the Boötes Void, the seam we read earlier as a relic, is exactly what the merger picture predicts. The last threads of an old dividing wall, caught mid-vanishing in the center of a hollow that used to be two or three. The void's interior isn't blank. It carries the scar of its own assembly, a faint internal structure that maps where the separate hollows once met. This is what lifts the merger idea above a merely convenient story. It made a prediction that a merged void should keep the ghost of its old walls inside it, and the ghost is there, threaded right through the middle, exactly where it ought to be. This turns out to be how voids grow in general, not just this one. They build hierarchically. small ones combining into larger ones over time, the mirror image of the way matter clumps from small lumps into great clusters. Run the clock forward, and the voids of the universe keep eating their dividing walls and merging upward, a few small hollows becoming one middling hollows joining into great ones. The Boötes Void sits high in that hierarchy, a grand union of many smaller emptinesses, and its internal threads are the family tree of everything it absorbed to get that big. An elegant symmetry hides in that. The way voids merge upward is the exact mirror of the way matter clumps upward, the same branching family history running in both directions at once. Small clumps of matter join into bigger clumps, and the same mathematics, with the density simply flipped, describes small voids joining into bigger voids. The cosmic web and its hollows are two versions of one process, structure assembling itself by merger, told once in the language of fullness and once in the language of emptiness. The clusters have their family trees of past mergers. So, it turns out, do the voids. Not every small void gets to grow, though. A void's future depends on the neighborhood it forms in, just as a galaxy's does. A small hollow that happens to sit inside a larger, underdense region is safe. The emptiness around it is also spreading, so it merges upward, joining the growing void. But a small hollow that forms inside a denser region meets the opposite fate. As the matter around it collapses inward, it squeezes the little void shut, crushing the emptiness out of existence before it can ever grow. Voids don't only merge. Some of them are killed, pinched closed by a crowding that closes in from every side. The great surviving voids are the ones that had the luck to form inside emptiness, where nothing was collapsing to crush them. And the Boötes Void hasn't finished assembling. It is, in all likelihood, still merging, still drawing the matter off its last internal walls, still reaching toward whatever smaller hollows lie against its edges. The scar through its middle is a wound mid-healing, the seam slowly dissolving as the final threads of the old wall drain away. Give it long enough and the interior will smooth out completely, the evidence of its piecemeal origin erased, leaving a single clean hollow with no memory of having ever been many. The seam can even be read like a clock. A merger long finished leaves only the faintest internal trace, its old walls nearly fully drained, the interior almost smooth. A merger more recent leaves a bolder thread, a wall caught earlier in its dissolving. The prominence of the scar running through a void is a rough measure of how lately it came together. Read that way. The strong central thread of the Boötes Void hints at an assembly not so very long ago, in cosmic terms. A great hollow that became one relatively late, it seems still fresh enough to show. Faced with something enormous, we reach for an enormous cause, a single grand event that made it. The largest emptiness in the known universe turns out to have no such cause. It was built quietly, collectively, out of many small and unremarkable hollows that simply happened to grow next to one another and join. Its bigness is not the work of one heroic region overreaching. It's an accumulation, a sum of the ordinary, the way most large things in the universe actually come to be. And the only reason we can tell the story at all is the scar, the faint internal seam the assembly forgot to fully erase. The merger closes the gap the clock had opened, and the void's origin finally hangs together, seed to runaway to union, a single unbroken account of how a piece of almost nothing became the emptiest place we know. But every step of that account has the same thing at its heart. A faint difference, amplified. A faint difference, amplified and then combined. From the first quantum ripple to the last merging wall, the whole story runs on one quiet engine, the relentless growth of unevenness that began almost too small to exist. So, what does it mean that all of it, the walls and the hollows, the galaxies and the great voids, and the matter that became us, was built out of differences that, at the very start, barely rose above nothing at all? It means that everything owes itself to imperfection. A universe that began perfectly smooth, matter spread with flawless evenness everywhere, would have stayed that way forever. Nothing to gather around. No place fuller than any other for gravity to favor. No galaxies, no stars, no planets, no voids, and no one anywhere to notice the lack. A perfect universe would have been a dead one. Everything that exists, the walls and the hollows and the worlds and the watchers, traces back to the fact that the early universe was not quite even, and that the unevenness was never going to stay small. And that smoothness could not have lasted, even if it had been perfect. A uniform spread of matter is balanced, the way a marble is balanced on the very top of a hill, holding still only as long as nothing touches it, and bound to roll the instant anything does. Gravity makes evenness unstable. The faintest excess pulls a little harder and grows. The faintest deficit holds a little weaker and empties. There is no nudge too small to be amplified, given enough time. So the structured universe wasn't added to a smooth one later. It was already latent in the smoothness, waiting in the instability for the first ripple to set it rolling, and the ripple was always going to come. Step back far enough, and you notice that difference is the only thing that ever does anything. Everything we point to and call a thing is really a place that differs from what surrounds it, a region denser or hotter or more ordered than the average around it. Perfect sameness is inert. It has no edges, no features, nothing to push against anything else. A star is a difference in density. A planet is a difference. So, in its own way, is a void, a difference in the other direction. The universe is not made of stuff so much as of contrasts, and where everything is the same, in the deepest sense, nothing is there at all. A strict accounting sits underneath this too. The matter that gathered into the walls and the clusters had to come from somewhere, and where it came from is the voids. Every dense place in the universe is paid for, exactly, by an empty one. The fullness of a galaxy cluster is the precise measure of the emptiness of the hollows that fed it. So the void isn't waste, or leftover, or the part that didn't get to be something. It's the necessary other side of the ledger, the debit every bright structure was written against. You cannot make a crowded universe without making an empty one in the same stroke. The walls and the voids are not two things. They're one act of sorting, seen from its two ends. This is the single rule running under the whole story we followed. Take a near-perfect evenness, lay the faintest unevenness across it, and let gravity amplify the difference without rest. That one process, applied for billions of years, made all of it. The galaxies are where the difference ran one way. The voids are where it ran the other. The seed of the Boötes Void and the seed of our own galaxy were the same kind of ripple in the same smooth field, sorted only by sign, and everything that came after, the draining, the merging, the slow flowering of structure, is that one rule playing out at every scale at once. A deeper current runs under even this. The smooth early universe was a peculiar starting point, an ordered, low-entropy condition that gravity has been spending ever since. Left to most forces, things even out over time, smoke filling a room, heat spreading until everything matches. Gravity runs the other way. It takes the smooth and makes it lumpy, and that clumping, that steady growth of difference, is bound up with the very direction of time, the slow unfolding from an even beginning toward an ever more structured present. The building of the voids and the walls isn't a side effect of the universe aging. It's part of what aging, for a universe, even means. The amplifying is the solid part, watched directly in the growth of structure and reproduced in every simulation we run. The deeper question, where the very first unevenness came from, is the one still partly open, traced most likely to the quantum restlessness of the infant universe, but not yet nailed down beyond all doubt. We know, with confidence, that difference was amplified into everything. Exactly why there was any difference to begin with is the question still being worked, the one loose thread at the bottom of an otherwise tight account. There's something in this worth carrying out of the astronomy, though it isn't a lesson the universe meant to teach. We tend to prize evenness, symmetry, the smooth and the balanced, and to treat imperfection as a flaw to be corrected. The universe runs the other way. Its smoothness was barren. Everything it ever made, every structure, every light, every living thing, is the descendant of a blemish, a place where the perfect evenness failed by 100,000th. We are, quite literally, the children of an imperfection, a slight excess that gravity took and grew. And the great void is its sibling, the slight deficit on the other side of the same flaw. Perfection would have left the universe empty. It was the imperfections that filled it. A quiet necessity is folded into that, as well. A universe smooth enough to be perfect would also be a universe with no one in it to call it perfect. Observers are themselves amplified differences, knots of structure that only an uneven cosmos can grow. So any universe that gets noticed at all has to be one of the flawed ones, the kind whose smoothness failed. We were never going to open our eyes in a featureless cosmos and admire its evenness. The only universes that produce eyes are the imperfect ones. The flaw isn't only where we came from. It's the price of there being anyone at all to ask about it. The whole vast architecture, the bright threads and the dark hollows, the clusters and the great voids, came from differences that, at the start, barely rose above nothing. A whisper of unevenness, patiently amplified, became a universe. And somewhere in that flowering of small differences into large ones is the matter that became the body lying here in the quiet, itself a difference made large, a faint excess in an ancient field that grew, against all the smoothness around it, into something that could wonder where it came from. One rule, then, made all of it. But it ran on a field of differences that were essentially random, and a single rule turned loose on a random field doesn't produce one result. It produces endless variety. No two galaxies came out the same, and no two voids did either. The Boötes Void is the largest and emptiest we know, but it is one member of a whole family of hollows, each shaped by its own seeds, its own neighborhood, its own history of merging. So, if every void is the child of the very same law, why is no void quite like another? And what does the rest of that family look like? Voids are not a type. They're a family, and like any family, they vary more than the shared name suggests. They come in a great range of sizes, from small hollows only tens of millions of light-years across, scattered thickly through the cosmic web, up to rare giants hundreds of millions of light-years wide. They differ in how empty they are, some merely thin, some deeply drained. They differ in shape, some nearly round, some lumpy and irregular. And they differ in what they hold inside, some smooth, some threaded with the relic walls of old mergers. The Boötes Void is one member of that family, not the whole of it, and it is far from typical. A few faces help. The local void sits right beside our own group of galaxies, and we'll come to it in a moment. Other named giants are scattered across the surveys, great hollows in the direction of Canes, Venatici, and elsewhere, each with its own size and character. And on still larger scales lie vast, contested underdensities, the kind that may stretch across a sizable fraction of everything we can see, which we'll meet shortly too. The Boötes Void is the famous one, the textbook example, but it has plenty of company, and not one of its companions is quite like it. One law made all of them, but a single law turned loose on a random field doesn't repeat itself. The seeds varied. Some began as deeper dips in the early smoothness, some as shallower ones. The neighborhoods varied, some hollows forming inside larger emptiness and free to grow, others caught in denser surroundings and squeezed shut. The merger histories varied, some voids assembled from many smaller ones, some still nearly single. It's the way one species of tree, planted across different soils and weathers, grows into 1,000 different shapes, all unmistakably the same kind, no two alike. Same rule, different luck, endless variety. The variety reaches all the way down into what the voids hold. The galaxies inside a shallow void aren't quite like those in a deeply drained one. The deeper and emptier the hollow, the more isolated and undisturbed its few residents, the more extreme the gentleness we traced earlier. A void's depth sets the terms of life for everything in it. So the family isn't only a range of empty spaces. It's a range of conditions, each hollow offering its handful of galaxies a slightly different degree of solitude, a slightly different pace for the slow, undisturbed existence we followed before. What sets the Boötes Void apart isn't really its size, though that's the headline it usually gets. There are regions of the universe that span as far or farther. What makes it remarkable is the combination of size with depth, how thoroughly emptied it is for something so large. Plenty of big regions are only gently below average. Few are both this big and this deeply drained. The Boötes Void is striking less for its width than for how little it managed to keep across that width, a large hollow that is also, for its size, a remarkably thorough one. Draining a region deeply takes time and work, and the larger the region, the harder it is to empty it far. So the deepest voids tend to be the smaller ones, thoroughly cleaned out because there wasn't so much to clear. The very largest regions, by contrast, are usually only mildly underdense, broad, gentle dips rather than true hollows, because nothing could have drained something that vast to any real depth in the time available. The Boötes Void sits in an uncommon spot on that trade-off, large enough to be a giant and yet emptied far enough to be a true void, which is part of why it drew such attention in the first place. Some of the Boötes Void's fame is an accident of timing. It was among the first great hollows ever found, named and studied, while the very idea of cosmic voids was still new, and that early dramatic arrival fixed it in the textbooks as the void. Whether it is truly the single largest or emptiest in all the sky is a harder claim, and probably not one worth defending too fiercely, since larger and stranger underdensities have turned up since, and the answer shifts with every survey and every choice of how to measure. Its real distinction isn't a trophy for being biggest. It's that it was the one that first taught us this whole family existed at all. The family splits in kind too, not only in degree, and the distinction matters more than it sounds. A void in the strict sense is a sharp, well-bounded hollow in the cosmic web, a region clearly emptier than the walls that ring it, like the Boötes Void. But the same loose vocabulary gets stretched to cover something quite different, a broad, gentle, large-scale region that is merely a little below the cosmic average over an enormous span, with no sharp walls and no clean emptiness, just a vast, shallow dip. Both get called voids, or supervoids, or underdensities, the words traded almost interchangeably. They are not the same object. One is a hole. The other is more like a slow, wide shallowing of the whole sea floor. The boundaries between void and supervoid and underdensity are not written into nature. They're conventions, lines we draw at chosen thresholds, and the same region can be classed one way or another depending on how strictly you measure and how large a box you draw around it. The family has fuzzy edges, not only between its members, but in the very definitions we use to sort them. A clean taxonomy is something we want more than something the universe hands us. For all that looseness, the family as a whole is one of our sharper tools. The number of voids of each size, how many small ones, how many giants, the whole distribution of emptiness across the sky, is something our models predict in detail, and something we can go out and count. If the universe produced far more giant voids than the rules allow, or far fewer, we would know the rules were wrong. So the messy, fuzzy-edged family, taken together as a population, becomes a precise test, the catalog of hollows weighed against the theory that should have made them. The individual names may be sloppy. The census is not. There's a habit at work in all of this, and it's an old one. We meet a handful of strange new things, and we reach for a single word to hold them, and the word, once it sticks, quietly tells us they're all the same. Void does that. It files a sharp hollow in the web and a vast shallow dip in the mean, and a merged giant scarred with old walls all under one calm syllable, as if they shared more than they do. The truth is that the family of emptinesses is as varied as the family of bright things, with as many different origins and futures, and the single name we hung on all of them hides almost all of it. So the voids are not one thing repeated. They're a scattered population of hollows, each shaped by its own seeds and luck and history, strung through the dark in every size and depth. But of all of them, the one that matters most to us isn't the largest, or the emptiest, or the most studied. It's the nearest. Because we are not standing outside this family, examining its members through a telescope from some neutral distance. We live inside the cosmic web, pressed up against the edge of a hollow of our own. So which void is closest to home, and what has it been quietly doing to us all along? The nearest void isn't far away at all. It begins right at the edge of our own cosmic neighborhood, close enough that we don't really observe it so much as live against it. It's called the local void, and our galaxy, along with the small crowd of galaxies it belongs to, sits on the rim of it, the way a town can sit at the edge of a wide, empty plain. On one side of us, the local gathering of galaxies. On the other, the local void, opening out into a great nearby emptiness we have been beside for our entire existence. It's a large hollow, not as grand as the Boötes Void, but substantial, a stretch of unusually empty space pressed right up against our own. Our local group, the handful of galaxies that includes the Milky Way and Andromeda and a few dozen smaller ones, doesn't sit in the middle of anything rich. It sits near a boundary, with denser structure on one side and the local void's emptiness yawning on the other. We are, in the most literal sense, a neighborhood on the shore of a hollow, and we always have been. What's striking is how empty our own backyard turns out to be. We might have expected to find ourselves somewhere ordinary, neither crowded nor bare. Instead, the region just beyond our local sheet of galaxies is one of the emptier patches anywhere nearby, a real hollow opening almost on our doorstep. We didn't end up in the thick of things. We ended up on the shore, with one of the family of voids beginning just past the edge of home. And the hollow hasn't left us alone. It's been pushing us, gently, the whole time. Our galaxy isn't sitting still in space. The whole local group is moving, drifting across the universe at hundreds of kilometers every second relative to the oldest light, and a large share of that motion is the local void at our back, shoving us away from itself toward the fuller regions ahead. We have been in motion our entire history, carried along in part by the emptiness we happen to live beside. A void can't actually push anything, though. It has less matter than its surroundings, not some special force that repels. What's really happening is subtler and stranger. Every direction in space pulls on our galaxy by its gravity, and those pulls would roughly cancel if matter were spread evenly. But matter isn't even. In the direction of the local void, there's less of it, so the pull from that side is weaker than the pull from everywhere else. The result is a net tug away from the void, toward the denser regions, exactly as if the emptiness were pushing us. The push of a void is really the absence of a pull on one side, the lightest side of an uneven tug-of-war winning by default. This isn't a guess we can't check. Our motion through space is known with real precision. The oldest light in the universe, that even glow again, looks very slightly warmer in the direction we're heading and cooler behind us, and from that faint lopsidedness, we can read our speed and our heading exactly. When we try to account for that motion, to add up what's moving us, part of it is the gravity of distant, dense regions far ahead, drawing us toward them. And part of it, a real and measurable part, is the local void behind us, the push of the nearby emptiness showing up plainly in the direction our whole galaxy travels. Recent maps of our motion have made the push clearer and stranger. When astronomers charted not just where we're going, but the full landscape of what pulls and pushes us, they found two influences working together. Far ahead, in the direction we're heading, sits a great concentration of galaxies, an attractor, drawing us toward it. And far behind, in the direction we're fleeing, sits a vast underdense region, a great emptiness researchers named for its single clear effect, a repeller, pushing us away by the same trick of underpulling. We are caught between a pull in front and a push behind, a crowd ahead and a hollow at our back, and both are carrying us the same way. The emptiness isn't a bystander in our motion. It's half the engine. This changes our standing entirely. Through this whole story, we've spoken of voids as distant objects, out there in the dark, studied from a safe remove. But we are not outside the family of hollows, looking in. We live in the cosmic web, on the edge of one of its emptinesses, and that emptiness has had a hand on us from the beginning. The void is not only a thing we observe. One of them is a near neighbor, steering us, deciding in part which way our galaxy drifts through the universe. We have been a void's neighbor all along, and it has been quietly setting our course. Every measurement we make of the universe's large-scale shape is made from this galaxy, and this galaxy is moving, shoved along by the local void and pulled by the crowds ahead. So our very first view of the cosmos came pre-tilted by our own motion, the whole sky faintly reddened behind us and blued ahead by the speed of our drift. Before we could map the universe straight, we had to find that drift and subtract it to take our own void-driven motion back out of the picture in order to see anything clearly at all. We never had a still place to look from. We had to discover we were moving and correct for it before the rest of the structure would come into focus. That nearby emptiness has shaped more than our motion. It's part of why our local patch looks the way it does, sparse toward the void and richer away from it, our small group of galaxies strung along a wall with a hollow at its back. The arrangement of our cosmic address, which way the galaxies thin out and which way they gather, owes a great deal to the local void sitting where it does. The emptiness hasn't only been pushing us. It's been quietly authoring the shape of the neighborhood we call home. The emptiness we've been treating as the most remote and abstract thing in the universe, a hollow studied at the very limits of our instruments, turns out to have a close cousin right next door, with its hand on our own galaxy. We have been moving away from a void for our entire existence. Every one of us carried on that slow drift, and not a single person has ever felt it. The steering is far too gentle and far too vast to register. But it's real, and it's been with us the whole time. The push of a nearby nothing we never knew was at our back. So even now, in the stillness, you are moving. The whole galaxy is, the whole local crowd of it, sliding away from the local void at hundreds of kilometers a second, carried by the simple fact that there's less to hold us back on one side than the other. It's the way you can sit perfectly still on a smooth, fast train and feel nothing of the speed, except that here the train is the galaxy and the track runs away from a hollow. It's a motion no body can feel, smooth and unbroken, a drift away from an emptiness we live beside. And if a void this close can move us without our ever noticing, a stranger question opens underneath it. What if we don't merely live next to a void, but inside one, a far larger and gentler hollow than this, vast enough to hold our whole corner of the universe? And if we did, would we have any way at all of telling, from the inside? The question has a real answer, or the beginning of one. Several teams of astronomers, starting in the early part of this century, began noticing something in the galaxy surveys around us. When you count the galaxies within about 1 billion light-years in every direction, and compare that count to what the average of the universe should look like, the number comes up short. Not dramatically short, not the way the Boötes Void comes up short, but measurably, persistently short. The region of space containing our own galaxy appears to sit inside a broad, gentle underdensity, a zone where matter is somewhat thinner than the cosmic average across an enormous span. One analysis, by Ryan Keenan, Amy Barger, and Lennox Cowie, put the shortfall at somewhere around 20% below average, possibly more, extending outward for hundreds of millions of light-years. If that holds up under scrutiny, we are not standing outside the family of voids and looking in. We may be inside one of its members, one so large and so gentle that we didn't recognize it as a hollow at all. Before going further, it's worth being exact about what this underdensity is and what it isn't. It is not a classic void of the kind we have been describing all night. The Boötes Void is a sharp hollow, deeply drained, with walls you could in principle point to. What the surveys around us suggest is the other kind, the one we distinguished earlier, a vast and shallow dip in the mean, spread across a region far larger than any classic void, with no clean edges and no dramatic emptiness inside, just a broad, slow thinning of the cosmic field over an enormous scale. The same physics made it. The same runaway of unevenness shaped it. But the result is a gentle basin, not a hole, more like that wide shallowing of the sea floor than a chasm cut in it. From the inside, a hollow like this would be nearly impossible to recognize by eye. A sharp void announces itself. The galaxies crowd up on the walls, the interior goes bare, and the structure is visible in any survey that reaches far enough. A broad, shallow underdensity doesn't do that. The thinning is too gradual to jump out. The galaxies near us look roughly normal. The dip extends so far in every direction that you'd have to map out to enormous distances before the outside average came into view to compare against. You'd have to be able to see, clearly and in detail, what the universe looks like beyond the edge of your local basin, and for most of human history, that view wasn't available. We can only be inside something this large and this shallow and not know it if it's large and shallow enough to contain everything we could easily see. The idea that we might live inside some degree of underdensity isn't, on its own, alarming. The cosmic web is lumpy. Some regions are denser than average and some are thinner, and by the basic logic of the situation, any given galaxy has to land somewhere on that distribution. We have no strong reason to expect our position to be exactly average, and a modest shortfall in local density is not a surprise. The uncomfortable part isn't the underdensity itself. It's a specific consequence it may be having on one of our most carefully tested measurements of the universe. We measure the expansion rate of the universe by two broad families of method. One uses objects in the relatively nearby universe, supernovae of a particular type, and pulsating stars whose distances we can calibrate, to build a distance ladder step by step out to where the expansion is visible. The other uses the very first light, the ancient glow, to infer what the expansion rate was set at in the early universe and predict what it should be today. For a long time, these two families roughly agreed. Over the past decade and a half, they have drifted apart, the nearby method consistently returning a higher expansion rate than the early universe method, the gap stubbornly persisting through every refinement and recheck, sitting now at a level too large to be comfortable and too persistent to dismiss easily. This disagreement is called the Hubble tension, and it is one of the real open problems in cosmology. If our galaxy and everything we use for our nearby measurements sits inside a region that is somewhat below the cosmic average in density, then the expansion of space around us could be running slightly faster than the cosmic average. A thinner region expands a little faster, for the same reason a void expands faster internally than the denser cosmic web around it. And if local expansion is biased upward by even a few percent, our nearby expansion measurements would come out too high relative to the true cosmic rate, possibly enough to account for at least part of the gap with the early universe measurements. We might, in other words, be inside a gentle underdensity that has been quietly tilting one side of a very important scale. This has to be held carefully because it is contested, and contested on multiple fronts. The size and depth of the local underdensity are themselves not settled. Different surveys and different methods give somewhat different answers, and the agreement isn't clean. And even taking the underdensity at its most generous estimated depth, most analyses suggest it can account for only part of the Hubble tension, not the whole of it. There are other proposed explanations: new physics in the early universe, unknown systematic errors in the measurements, extensions to the standard model, each with its advocates and its problems. The underdensity isn't established as the answer. It's one piece of a puzzle that doesn't yet have an agreed solution. What lingers after the careful accounting is an epistemic unease, a real one. We saw earlier that we had to discover our own motion, subtract the local void's push, before the structure of the universe came into focus. The implication now is that there may be a further layer of that, a larger, more subtle tilt in our vantage that we are still working to identify and measure. Every nearby measurement of the expansion rate is made from inside whatever local density we actually inhabit, and the local density shapes what those measurements return. We have learned to correct for our motion. Whether we have fully corrected for our position is the question the underdensity raises and hasn't yet answered. The same standard applies here. The underdensity, if it's real at the scale suggested, is a soft puzzle, the kind that adjusts numbers and shifts calibrations, not the kind that breaks the underlying physics. The laws don't change inside a gentle basin. The universe outside it would look the same. It would mean our local rulers were slightly out of step with the cosmic average, not that the cosmic average was wrong. It would be a calibration problem, a significant one, but the correctable kind, the sort of thing that gets absorbed into better measurements and larger surveys as our reach extends. There's something quietly fitting about where this leaves us, though. We began the night with the Boötes Void, a hollow we could point to on a map, out there in the constellation of the herdsman, remote and extraordinary. And we arrive here with the possibility that the emptiness isn't only something we observe at arm's length. It may be, in some gentle and much larger form, something we're inside of. We have been looking at voids all this time, and there may have been one all around us. The question remains open, the underdensity real but its size uncertain, its effect on our measurements possible but unproven, no verdict yet in hand. But the possibility alone changes the view. It makes the emptiness personal in a way that pointing at a distant map never quite did. So if we do live inside something like a void, however shallow, what does it actually feel like to live beside emptiness? And what does a life built on the edge of a hollow look like from the inside? Living beside emptiness looks, from the inside, like nothing at all. That's the honest answer to the question we arrived at. There's no signal, no sensation, no quality of the air or the light or the weight of things that carries any trace of the hollow pressing up against our neighborhood. The local void has been our nearest large-scale neighbor for the entire life of this planet, and nothing about ordinary existence on its shore has ever announced that fact. You could spend a lifetime looking at the sky and find no obvious sign of it. The void doesn't show. And yet it authored the shape of our address more thoroughly than anything we can see. The region of galaxies we call home isn't centered or neutral. It leans. The local sheet of galaxies we belong to, the Milky Way and its neighbors arranged in a flattened structure, runs roughly along the boundary between the void's emptiness and the richer structure on the other side. That arrangement is not a coincidence. The void pressed in from one direction, matter gathered more thickly from the other, and our local cluster of galaxies settled into the shape that the tug-of-war between those two directions produced. The way our cosmic neighborhood is laid out, which side is sparse and which side is dense, which way the galaxies thin out and which way they stack up, is a direct record of the void sitting where it does. The motion we carry is the void's work too, the quiet push we described before, hundreds of kilometers every second away from the local void and toward the denser structures ahead. Every living thing that has ever existed on this planet has been carried on that drift. The whole Earth, the whole solar system, the whole galaxy, sliding away from a nearby hollow since before there was biology here to slide. Not one of them felt it. Not one had any way to know. The motion is too smooth and too vast to register as motion at all. The way a person asleep on a ship crossing a calm ocean feels nothing of the speed. What strikes me about this, having spent time in the details of it, is how long the void stood behind everything without appearing in any of the pictures. Every civilization that looked up at the sky looked up from this shore. Every astronomer who trained an instrument at the night sky trained it from a position on the rim of a hollow. The ancient catalogs of stars, the first maps of the nearby galaxies, the early surveys of the large-scale structure, all of it was done from here, adjacent to an emptiness that simply never showed up in the results, not because it wasn't real, but because counting nearby stars and plotting nearby galaxies doesn't give you the scale you need to see it. The void requires a particular kind of looking, one that reaches far enough to sample what the universe looks like on average, and that looking only became possible recently as surveys grew deep enough to count faint galaxies out to distances of hundreds of millions of light years. The hollow was always there. The instruments that could reveal it took most of human history to build. We look from somewhere. Every survey, every measurement, every catalog starts from the patch of the universe we happen to occupy, and the patch shapes what we can easily see and what stays hidden until we look harder. The local void hid not by concealment, but by scale. It was too large to fit inside the view we had for most of the time we were looking. Our position was always a fact about our science, even before we knew our position well enough to account for it. What the void does show up in, once you know to look, is the sky itself. The direction toward the local void is a quieter direction. Fewer galaxies in that patch of sky, a sparser field when the surveys are deep enough to see it, the emptiness leaving its mark, not in what's there, but in what isn't. The distribution of galaxies across the sky is not even, and some of that unevenness is the void at our back, thinning the view in one direction while the denser structures ahead populate the other. The void is in the map of the sky, quietly, if you know which asymmetry to trace. To live beside it is, in this sense, to live with a feature of your address that only shows up in the aggregate. A single glance at the sky doesn't reveal it. A single night of observing doesn't catch it. It takes the patient accumulation of thousands of galaxy positions, the slow building of a three-dimensional picture, to let the hollow come into view, and even then it appears as an absence, a region thinner than the average, which is the quietest way anything can announce itself. The void is always going to be the thing you find after you've mapped everything else, the shape left over when the bright things are all accounted for. There's something about that which fits the hour. The most significant features of a place aren't always the loudest ones. The hollow that steered our galaxy, arranged our neighborhood, and possibly tilted some of our measurements of the universe made itself known by what it lacks. Not by mass or by light or by any signal a body could detect, but by a patience in the counting, a shortfall in the average, a consistent thinning that only a long look reveals. It is, in a way, the kind of presence that only becomes visible when you stop looking for what's there and start asking what should be there and isn't. Which raises a question about the future of these hollows. Gravity is not the only thing at work in the universe. There is something else, something that gravity can't outrun indefinitely, and it has already begun to change the terms. Voids have been growing for billions of years by draining their matter outward, but there is now a second force pulling space apart faster than gravity can gather it, and in the emptiest regions, with the least gravity to resist, that force has the clearest field. Dark energy doesn't win everywhere at once. It wins first in the voids, the places that were already the least able to hold things together. So what happens to a void when even the expansion of space turns against it? Something has been pulling space apart faster and faster for roughly the last 5 billion years, and we don't know what it is. That's the honest starting place for dark energy, the name we give to whatever is driving the accelerating expansion of the universe. We know it exists because the evidence for it is built into the light of distant exploding stars, supernovae of a type that all reach the same peak brightness and so work as reliable distance markers. When Saul Perlmutter, Brian Schmidt, and Adam Riess analyzed those distant supernovae in the late 1990s, they expected the expansion of the universe to be slowing down, gravity gradually pulling the brakes on the outward rush. Instead, the supernovae were fainter than they should have been, meaning farther away than they should have been, meaning the expansion wasn't slowing. It was speeding up. Something was pushing space apart, and whatever it wasn't any force that had a name yet. The leading description today calls it a cosmological constant, a fixed energy density belonging to space itself, the same everywhere and at all times, a kind of pressure built into the vacuum that pushes outward without any source requiring it. Whether that description is the final word or only the simplest model that fits what we currently see is still an open question. Dark energy makes up something like 2/3 of the energy content of the universe by current estimates, and we have no agreed explanation for where it comes from, why it has the value it does, or whether it might change over time. We know what it does. We don't know what it is. That honest gap runs right through the center of cosmology. The term itself has a strange history. When Albert Einstein first wrote down his equations for the universe, he introduced a constant into them to hold the cosmos still, a term that would counterbalance the tendency of matter to collapse. When Edwin Hubble showed the universe was expanding after all, Einstein set the constant aside, calling it his greatest mistake. What the supernovae found decades later was that the universe isn't just expanding, it's accelerating. And the simplest way to account for that acceleration brought the constant back, not as a blunder but as a necessity. The thing Einstein invented to hold a universe still turns out to be the dominant force pushing it apart, and it is running most freely in the emptiest places it can find. What it does, however, is clear enough. It accelerates the expansion of space at large scales. And the place where that acceleration finds the least resistance is exactly where we've spent the night. In regions full of matter, gravity can still hold the day locally. A galaxy cluster is a gravitationally bound system, its members locked together by the mass they share, and the expansion of space on the scale of a cluster is too small a thing to undo what gravity has already gathered. The expansion pulls, but the binding pulls harder. The cluster stays together. Inside a void, that arithmetic runs the other way. There is almost no matter, which means almost no local gravity to resist the expansion. The few galaxies that manage to survive inside a great hollow like the Boötes Void are not bound together by much. They sit at enormous distances from one another, thinly scattered, sharing too little mass to hold each other in any strong grip. And so the expansion of space between them goes nearly uncontested. Dark energy doesn't need to overcome much, because there wasn't much there to overcome. The voids are where the acceleration finds its easiest work. The result is that the rare inhabitants of deep voids are being pushed apart faster than any other galaxies in the universe, carried away from each other by a space expanding more freely than it does anywhere denser. The gap between void galaxies is already enormous. It is also growing, and growing at a rate that will not level off. For the sparse residents of a hollow like the one we've been tracing, the universe is already more nearly empty than anywhere else, and the direction of travel is toward emptier still. There is a threshold in all of this that the void's inhabitants may already have crossed. When the expansion of space between two objects becomes fast enough, the space between them is opening up faster than light can cross it. Those objects can never again exchange a signal. They cannot observe each other. They cannot reach each other. They exist in cosmologically separate domains, and the separation is permanent, not because of any wall or barrier, but because space between them is simply opening too fast for anything to bridge it. Dense regions have most of their neighbors inside this threshold, bound together and reachable. Void galaxies have almost no neighbors to begin with, and the ones they have are retreating into permanent unreachability faster than anything in a richer region. The inside of the Boötes Void may already be a place where no two residents can ever, under any future circumstances, reach each other. The inside of the Boötes Void isn't only the most extreme environment we know today. It's a working model of where the rest of the universe is eventually heading. The condition that void galaxies are already close to, sparse light, accelerating separation, permanent isolation from neighbors, is the condition that the universe outside voids will gradually approach over a much longer time as dark energy continues its work. What the void shows now, the universe will show later. The hollow is not a strange exception to the ordinary cosmos. It's a preview, running ahead of schedule. Every moment that passes, the void's internal expansion pulls its few inhabitants a little further apart, and the threshold of permanent isolation draws a little closer for any two of them that haven't already crossed it. Dark energy doesn't rest in the voids. It has the field almost entirely to itself there, running unopposed, pressing the already wide gaps wider, deepening the already deep silence. The void didn't simply stop growing when gravity ran out of time. It found a second engine, one that will outlast the first, one that doesn't depend on the kind of seeding and runaway that made the hollow in the first place. The second engine changes the character of what the void is becoming. In its early history, the void grew by shedding matter outward, a slow drain that emptied it from the inside out. Now it grows by stretching, space itself expanding faster inside the hollow than outside it, the isolation deepening not because matter leaves but because distance grows. The mechanism shifted at some point in the past few billion years, from draining to stretching, from an emptiness caused by matter fleeing to an emptiness enforced by space pulling itself apart. And the void, because it resists so little, stretches more than anything around it. It is the place in the universe where the future arrives first. So the arc bends toward a long, accelerating emptying, a process that won't stop when the last wall is drained or the last merger is done. It's already underway, already building on itself, already turning the hollow into something deeper and more permanent than what gravity alone produced. And over truly vast stretches of time, that process will not stay confined to the voids. It will spread, as dark energy keeps its pressure on everything everywhere, until the condition the void already knows becomes the condition the whole universe has to reckon with. So what does the far end of that arc look like, when the drying out has run as far as it can run? The far end of the arc doesn't look like an ending in any dramatic sense. No final flash. No boundary crossed where the universe suddenly stops. What the standard picture gives us is closer to an exhaustion, the slow burning through of a finite supply that was never going to last forever. The universe is running on its reserves of gas, the raw material for stars, and the reserves are being used up without being replaced at the rate they're being spent. The drying out is not a future event. It has been underway since the cosmos was a few billion years old, and we are living in what will eventually be remembered, if anything remains to remember, as the peak of it. Star formation reached its highest rate several billion years ago. Since then, the overall rate has been declining, not because the physics changed, but because the gas is going. Every star that lights up consumes some of what was available, fusing hydrogen into heavier elements and locking them away in stellar remnants when it dies. The universe has no mechanism for reclaiming that locked matter and cycling it back into fresh stars on the timescales that matter here. What gas remains will make more stars, and those stars will burn. And in time, the last of the raw fuel will be in the last stars, and then it will be in whatever those stars leave behind. There is a fixed amount of material to work with, and the process of working with it is itself the process of running out. The stars that remain the longest won't be anything like the Sunday. Massive, luminous stars are profligate with their fuel, burning so brightly that they exhaust themselves in millions of years, a fraction of a blink in the span we're considering. Stars like the Sun have a more moderate pace, measured in billions of years. But the longest-lived stars are the smallest and coolest, the red dwarfs, so dim and so slow in their burning that a single one can sustain its nuclear fire for something like 1 trillion years. They outnumber every other kind of star, and they will outlast everything else by margins that make the present age of the universe look like a preface. If the stellar era of the universe has a duration, most of it lies ahead, written in the long, slow output of stars too faint to see with the unaided eye. The brightest things we know are the shortest lived. The last lights will be the ones we barely notice. The universe is roughly 14 billion years old. A red dwarf can burn for something like 1 trillion years, which is about 70 times that age. So the time from now until the last red dwarf dies is, on the scale of what's already passed, like discovering that you're at the first page of a book that runs to 70 volumes. The present is not the middle of the stellar era. It is startlingly early, one of the opening chapters of a story that still has almost all of its pages unread. There's something in that which is difficult to absorb, not as a philosophical position, but as a simple fact about where we are in time. Every star we can see tonight, every galaxy, every bright thing in the night sky, is part of an era that is, by the universe's own measure, still very young. The whole of human history, every civilization, and every century of looking up has happened in the first fraction of 1% of the stellar age. We arrived at the party so early that the party has barely started, which means we are also among the least likely kind of observer, one who happens to exist before nearly all the time there will ever be has elapsed. After the last red dwarf fades, the universe doesn't end. It enters a long, dark, cold chapter whose timescales dwarf the stellar era, the way the stellar era dwarfs a human lifetime. What remains is the graveyard of stars, white dwarfs slowly cooling toward the temperature of the surrounding space, neutron stars locked and still, black holes waiting. These remnants don't shine. They drift in expanding darkness, growing colder and farther apart, gravitational ghosts of the things that burned. This is not a violent age. It is a very quiet one, the universe redistributing its heat across the widening space until the differences that drive any process grow too small to matter. Black holes are the last significant objects, and they don't last forever either. A property of quantum mechanics implies that black holes should very slowly radiate energy, losing mass so gradually over such vast timescales that for any black hole we know about, the process is completely negligible today. A stellar mass black hole, left in empty space, would require a time with roughly 67 zeros after it, in years, to evaporate completely. The supermassive black holes at the centers of galaxies would need something closer to a number with 100 zeros after it. To give that some scale, the current age of the universe has 10 zeros. The gap between what we know and the end of black hole evaporation is so vast that no analogy does it honest service. It simply exceeds the range of anything the human sense of duration was built to hold. After the last black hole evaporates, the honest answer to what remains is that we don't know with certainty. The leading guess, in a universe governed by the standard picture of dark energy as a constant, is a state of maximum entropy, an equilibrium so thorough that no process can extract usable energy from any difference because no difference remains. Not silence in the way we understand silence, but the deep physical condition where nothing can happen because nothing is different enough from anything else for any change to take place. Heat death is the name for it, a technical term that misleads a little because there's no heat left to speak of. It's more like the final averaging out of everything, the universe settling into the smoothness it started with, but a cold and empty smoothness with nothing left to build. Its few inhabitants are isolated. Its space is stretching without resistance. Its matter is thin and cooling and dispersed. The Boötes Void today is an advanced draft of the universe in its very late age. The condition everything trends toward written in the present tense, visible now through a telescope rather than after trillions of years of waiting. The hollow isn't just where dark energy wins first. It's where the far future is already being lived. Whether that is the actual ending, though, depends on an assumption we haven't tested enough to be certain about. The standard picture assumes dark energy is a constant, the same pressure everywhere and always. But if it isn't, if it changes over time, if it grows rather than holding steady, then the ending is different and more sudden. That possibility is the second branch, the one where the quiet drying out is replaced by something else, and the universe doesn't simply exhaust itself but is instead taken apart, down to its smallest pieces, by the very force that spent billions of years emptying the voids. The ending depends on a single number we haven't measured precisely enough. Everything in the long drying out assumes dark energy behaves like a cosmological constant, the same pressure everywhere and always, not growing, not shrinking, just persisting at the same value for all time. Under that assumption, the drying out continues without a dramatic finale, the universe cooling and quieting until nothing is different enough from anything else for any process to run, and that's the end. Heat death. The final averaging out. But there's a second possibility that the data haven't ruled out, one that changes the endpoint entirely. Dark energy might not be a constant. It might be something with its own dynamics, something whose strength varies over time, and specifically something that could grow. The simplest way to parameterize this is a number physicists call the equation of state, a ratio describing how the pressure of dark energy relates to its energy density. For a true cosmological constant, that ratio is exactly -1. For some kinds of dynamic dark energy, including a class called phantom energy, the ratio is slightly more negative than that. The difference sounds technical and small, and in the current universe, the effects are barely distinguishable. But over time, the difference in behavior is enormous because a growing dark energy doesn't plateau. It compounds. If dark energy grows rather than holds steady, then at some point in the future, it stops merely accelerating the expansion of space and begins to overwhelm every other force. Gravity, which holds galaxies and solar systems together, would be the first to lose. Gravitationally bound structures would find the expanding space between their members growing faster than their mutual gravity could resist, and they would be pulled apart. Not violently, at first, but inexorably, the binding loosening over time as the growing pressure outpaces the pull. Galaxies would disperse. Then, as the pressure grew further, solar systems, smaller and more tightly bound, would follow. Then planets. Then the structures of matter itself. The cascade moves down through the scales of binding. Atoms are held together by electromagnetic forces, far stronger than gravity across short distances. Those forces would resist longer. But if dark energy keeps growing without limit, it eventually overwhelms them too, the electron stripped from its nucleus, the atom dissolved into its parts. Then the nuclear forces, the strong interactions that hold protons and neutrons together in atomic nuclei, would be next, and the nucleus itself would come apart. The cascade would end, if any end can be specified, in a final moment where even the fundamental constituents of matter can't hold together, a moment sometimes described as the last threshold of the rip, after which nothing bound remains. This is what gets called the Big Rip, a scenario first worked out in detail by Robert Caldwell, Mark Kamiankowski, and Nevin Weinberg in the early 2000s. The void is where this would be felt first, by the same logic that made it where dark energy wins first under current conditions. The sparse inhabitants of a deep hollow like the Boötes Void are already the least gravitationally bound structures in the known universe. If dark energy begins to grow, those already loosely held residents would be the first structures to be pulled beyond the point where their mutual gravity has any remaining claim on them. The rip would move from the least bound to the most bound, from the hollows outward to the walls, from the walls to the clusters, from the clusters down through solar systems and planets, and eventually into the bodies of matter itself. The void, which began as a place of exceptional emptiness, would become the leading edge of the universe's final unraveling. The honesty required here is that we don't know which branch is the real one. Current observations are consistent with dark energy being very close to a constant, the ratio very close to -1, but the measurements aren't precise enough to confirm which side of exactly constant the truth sits on. A ratio just slightly more negative than -1 gives a big rip. A ratio of exactly -1 gives heat death. The difference is immeasurable at current precision, and the consequences are cosmically different. We are in the position of someone who can see that a fork in the road is coming but can't yet read which way the signs point. One of the stranger positions to be in is knowing two possible endings clearly, being unable to distinguish between them from where we stand, and having both of them be so remote in time that no consequence of either reaches us in any practical sense. The timescales for both endings exceed the current age of the universe by factors that dwarf anything in ordinary experience. Whatever the conclusion turns out to be, it lies in a future so distant that every civilization that will ever exist might have come and gone before the question is answered by the universe itself. We are working this out from the very beginning of the time available to work it out. There are other proposed endings too. Cyclic models that have the universe bouncing rather than concluding. Quantum effects at late times that produce unexpected behavior. Scenarios that reopen the question of what happens after maximum entropy. None of these are established. They are the speculative edges of a field that is itself still young, possibilities that honest theorists entertain without committing to. The two most observationally motivated scenarios remain the quiet drying out and the growing rip, and between them, the data currently say only that both remain possible. What the two endings share, despite their different characters, is more striking than what separates them. In both, the universe is not permanent. Whether it trails off into the final cold averaging or is taken apart down to its constituents, it is not the kind of thing that lasts forever. This is a strange fact to know. For most of human history, the sky above was simply the sky, permanent in any sense that mattered, the stars fixed or nearly so, the universe assumed to be simply there, without a trajectory or an arc. Now we know the arc, at least in outline, even if the last chapter is still unresolved. The universe has a story, and we can see enough of its shape to know it has an ending, even while the exact ending eludes us. That knowledge arrived recently, in the span of human generations, through instruments sensitive enough to read the dimming of distant supernovae and the distribution of ancient light. And the fact that it arrived at all, that minds in this corner of the universe put together enough of the picture to see an ending coming, raises something that only comes into focus when you stand back far enough from all the science. The universe will spend the overwhelming majority of its existence on either timeline in a state that precludes observation of any kind. The cold, dark era after the last star is not a time of knowledge. The time of knowledge is now, and it is brief. So, how brief is it exactly, and what does it mean that we happen to exist inside it? The window is brief in a way that takes some setting up to see properly. Start with what we established about the stellar era. Stars will exist, in some form, from now until roughly 1 trillion years from now, when the last red dwarfs finally exhaust their fuel. The current age of the universe is about 14 billion years, which means we're somewhere around 1% of the way through the stellar era. Not near the middle, not past the prime. At the very beginning, in any reckoning that takes the full arc seriously. But the window for observers isn't quite as long as the stellar era itself. Complex chemistry, the kind that assembles into living things, requires elements heavier than hydrogen and helium, carbon and oxygen, and iron, and the rest of the periodic table. Those elements don't come with the universe. They're forged in the interiors of stars and scattered when those stars die, seeded across space to be gathered up by the next generation of forming worlds. The very first stars in the universe were made almost entirely of hydrogen and helium, because nothing heavier existed yet. They had to live and die before the raw materials for planets and chemistry, and eventually biology could even be available. The earliest possible moment for observers is not the beginning of the stellar era. It's some generations after that, once enough stars have lived and died to build a universe with the right chemistry in it. The late stellar era may also narrow the window from the other direction, though this is less certain. Red dwarfs are dim, and whether their faint, long-lived warmth provides conditions suitable for biology is debated and unresolved. The most comfortable stretch for the kind of complexity we know about is the middle portion of the stellar era, the age of sun-like stars with well-lit planetary systems, of which the current epoch is part. Whether the era of the last red dwarfs is an extension of that window or a closing of it is something we can't yet say with confidence. What we can say is that after the stellar era ends, the window closes hard. The degenerate era, the long age of cooling white dwarfs and silent neutron stars and waiting black holes, provides no energy gradients of the kind that life as we understand it requires. The black hole era, with its extraordinary timescales, is darker still. The dark era that follows is a cold and expanding emptiness with no structure capable of forming or sustaining anything. The overwhelming majority of cosmic time, by any reckoning, is not a time of observation. It is a time of nothing in particular happening on any scale that observers would recognize as interesting. The window for knowing things about the universe is confined to the thin layer near the beginning of the total available time, and we are in that layer now. To put some numbers against it, imperfectly, compare the length of the stellar era, roughly 1 trillion years, to the length of the black hole era, with its timescales measured in numbers with 60 or more zeros. The stellar era, long as it is a rounding error compared to the post-stellar ages. The window of possible observation is a rounding error within a rounding error, a thin band at the very start of a story that hasn't begun to show how long it really is. Something stops me in the middle of that, not as a response I'm performing, but as a plain fact that took time to actually register. The same observations that gave us the accelerating expansion, the dimming of the distant supernovae, also confirmed that the universe is young by its own standards. The discovery that the universe will expand forever and cool into silence also placed us squarely in its early, complex, observer-capable era. The two facts came together in the same data, from the same careful measurements. We found out we were near the end of the window's early reach and near the beginning of everything else, at the same moment, from the same instruments. The void connects to this in its own way. The galaxies inside the Boötes Void are already approaching the condition of post-stellar isolation. Their neighbors are retreating beyond contact. Their star formation is limited and their gas reserves thin. In the very long run, they are headed toward the same dark quiet that everything heads toward, but they are getting there sooner, dimming earlier, moving toward the cold era faster than galaxies in richer environments. The void is not only a preview of the universe's spatial future, it's a preview of its temporal future as well, a region where the stellar era is already thinning at the edges, the window of observation already narrowing in the most isolated corners. What it means to be in the window is, at its plainest, that the universe is still doing something. Stars are burning, galaxies are moving, structure is forming and merging and evolving. The web is still being written. The voids are still growing. The oldest light is still crossing the sky, carrying its record of the universe a fraction of a second after the beginning. None of this will be available to whatever comes later, if anything comes later. The cold, dark era has no observers, and it doesn't miss them. But from here, inside the window, there is a specific quality to knowing that the capacity to look is limited in time, that the universe is complex. Information-rich phase is not its permanent condition, but its brief one. The knowledge we carry right now, the maps and the measurements and the story we've been following, exists only because the window is still open. Close the stellar era. Let the last star cool. And there is no mechanism by which the history of the universe remains legible to anything inside it. The record doesn't simply go unread. It eventually ceases to be available at all, as the remnants drift farther apart, as the structures that held the evidence dissolve. We are at the moment when the universe is still readable, and we happen to have started reading it. So, given that the window is brief, and that we're near the beginning of it, and that the universe is already so old that most of what made us possible has long since happened, what can actually be known from here? And what does a vantage as constrained as ours allow us to trust? There is a wall around what we can see, and it isn't getting farther away. As the expansion of the universe accelerates, space between us and the most distant visible regions is opening faster and faster, and there are already places whose light will never reach us, regions that have always existed and always will, but that no signal from us will ever touch, and no light from them will ever land here. This wall isn't something we can move closer to by waiting. As time passes, more regions cross behind it, receding into permanent invisibility. The observable universe is not a fixed vault that we're gradually filling in with better instruments. It's a shrinking share of what's actually there, and we are already in the era when the shrinking is underway. This means something specific about the future of cosmic knowledge. Observers who exist, if any do, in the deep stellar future will have access to less evidence about the universe's history than we have now. Some of the ancient light we can still detect today will have receded beyond their reach. The distant structures we can still map will be gone from their sky. The record of the universe's early ages, still legible to us in the distribution of galaxies and the patterns in the oldest light, will be partially erased for any observer who comes much later. It's possible, on this account, that we are living near the era of maximum accessible knowledge, the time when the most evidence is still within reach before the accelerating expansion begins to take it back. The picture we have built of the cosmos, incomplete and uncertain as it is, may be fuller than any picture a future observer could build. Not because we are smarter or more careful, but because we are earlier, and the universe is still showing us things it will stop showing anyone who comes much later. The brief window isn't only brief on its far end. It's also in the direction of knowledge near its peak. What we do with a constrained vantage is infer. Inference from incomplete data is not a failure mode. It's the whole method. And the void taught us this most plainly. The Boötes Void wasn't found by seeing it. It was found by noticing that something that should have been there wasn't, by comparing a careful count of galaxies against a model of what the cosmic average should produce, and finding a deficit. The emptiness was diagnosed by its effect on expectation, the way a doctor can find something missing by reading what the body fails to do, not only by seeing what's there. We mapped the largest hole we know by reading an absence. The method worked. That same method runs through almost everything we've learned about the universe's hidden architecture. Dark matter has never been directly seen. It's inferred from the way galaxies rotate, the way light bends around clusters, the way structure forms faster than ordinary matter alone could drive. The inference is secure not because we saw the thing, but because the gap between what visible matter predicts and what nature does is too consistent, too precise, and too well corroborated from too many different angles to be dismissed. Dark energy was inferred the same way, from supernovae too faint for their distance, from a universe expanding too fast for its matter content. We built the most consequential picture of reality we have from what was missing, from what didn't add up, from the careful reading of what should have been there and wasn't. The discipline is harder than it sounds. To infer well from absence, you need a reliable model of what should be present, careful enough measurements to detect a real shortfall, and honesty about the gap between the two. You need to know whether the absence is real or whether your model of expectation was wrong. With the Boötes Void, it took years before the people who found it would commit to saying the gap was real, because the first assumption was that the survey had missed something, that the instruments had failed, that the expectation was fine and the measurement was the problem. Only when independent checks from different instruments and different angles kept returning the same emptiness did the deficit become undeniable. The void was not accepted as real until it had been refused several times. I find myself thinking about what it means to practice patience with absence. Not the kind where you wait for more data and then go looking again, though that's part of it. More the kind where you sit with the gap between expectation and observation long enough to really ask which one to trust and resist the pull toward whichever answer is more comfortable. The void was uncomfortable. A region that empty wasn't supposed to exist by the assumptions of the time. It took the willingness to follow the absence rather than explain it away before it told anyone what it actually was. The limits are real, and naming them is part of the method too. We can't know what's beyond the cosmic event horizon. We can't know whether the universe we observe is typical of all that exists, or whether our local region, possibly inside a gentle underdensity, skews our measurements in ways we haven't fully corrected for. We can't know the full distribution of voids across the unobservable universe, whether the Boötes Void is remarkable by the standards of everything that exists, or merely remarkable by the standards of what we can see. These aren't failures of effort. They're the fixed conditions of our vantage, the things that are unavailable to any observer in our position, at our time, constrained by the same physics that shapes everything else. And that is perhaps the most important output of the whole enterprise. Not a final picture, but a precise map of what the picture can and cannot show. We know what we've measured. We know how we measured it. We know, with some care, what assumptions went into the measurement, and which of those assumptions are well supported, and which are inferences from indirect evidence. We know what lies beyond our reach and roughly why. That combination, knowledge of what we know and honest accounting of what we can't, is not a consolation prize for not knowing everything. It's what reliable knowledge actually looks like. It's what the void took years to achieve for itself, and what the universe as a whole is still in the process of yielding. So if the word we keep reaching for, the word that names the void and the galaxies inside it, and, in some moments, the experience of living in this narrow window of knowable time, is a word we brought with us from something much closer to home, what does that say about the word? A single galaxy in the interior of the void, sitting in the catalogs with its distance and its morphology and its spectral classification, and somewhere in the description the word lonely surfaced, as if the catalog entry had feelings. We noted then that lonely was our word, not the galaxies. Now we've come far enough to ask what that actually means, and whether the reaching for it told us something, loneliness has a specific anatomy. It isn't simply the absence of others in the physical sense. A room can be empty without being lonely. An ocean in the early universe, before any star existed, was not lonely. Loneliness requires a subject, something that has known or imagined connection, that holds the memory or expectation of it, and that registers its absence as a lack. It requires something for the absence to matter to. A void galaxy in the interior of the Boötes Void has no such subject inside it. It has stars and gas, and the dark matter that shaped its formation, and a history written in its morphology, but none of those carry the capacity to notice that no one is near. The isolation is real. The loneliness is not. What the word actually describes, when applied to the galaxy, is a physical state, a condition of cosmological separation, of being far from neighbors in a way that limits the kind of gravitational interactions that shape most galaxies. That condition is objective and measurable. The word we chose for it, however, comes entirely from the inside of human experience. Lonely is one of the most purely interior words we have. It presupposes consciousness, desire, the sense of time that lets a creature register what it's missing. Apply it to a physical system and you're doing something strange, not quite a mistake, but not quite a literal description either. You're using the vocabulary of experience to reach across to the vocabulary of physics, hoping the bridge holds. Sometimes it holds well enough. When the people who first described void galaxies reached for words like lonely and undisturbed and pristine, they were making the galaxy legible in a way that purely technical language doesn't quite achieve. Saying a galaxy with low metallicity and irregular morphology in an underdense environment is accurate. Saying a lonely spiral in the deep void lands differently, carries the physical facts in a way that moves through the mind at a different speed and settles in a different place. The word worked as a bridge, and the bridge made the thing more approachable, which is something. The risk is in staying on the bridge too long. Lonely implies something is missing that should be there, implies a state that is worse than the alternative, implies the object would rather be otherwise if it could choose. None of those implications apply to the galaxy. It isn't suffering its isolation. Its star formation isn't grieving the absence of mergers. The particular path it's taken through cosmic history, undisturbed by collisions and tidal forces and the stripping of its gas, produced what it is. The isolation didn't diminish the galaxy. It let it remain itself. Lonely is the wrong frame if we let the word carry too much of its human meaning. There is a more exact word available, and the sciences use it alongside the effective one. Isolated, in the physical sense, means something specific and measurable. It means beyond the gravitational communication that shapes most galactic evolution, beyond the range where mergers and tidal interactions play a regular role, developing along an interior trajectory with few external perturbations. Isolated is a physical descriptor, carrying none of the emotional freight. It describes the condition accurately, without implying how the condition feels to the galaxy, because the galaxy doesn't feel anything about it. The difference between isolated and lonely is the difference between describing the state and projecting a response to it. Both words are sometimes used. One of them is doing more work than it should. Faced with something distant and alone by physical measure, the human response is to name it with a human feeling. Not because we forgot it was a galaxy. but because the human interior is the most detailed map of certain kinds of experience we have, and when we encounter something that shares even the physical structure of a human state, the vocabulary of that state is the fastest route to understanding. We project not to mislead, but to approach, to make the foreign thing legible by finding in it the shape of something we already know. The projection reveals more about the projector than the object, though, and that's worth following out. The fact that we call this galaxy lonely says something about what loneliness means to us, how central the experience of connection and its absence is to the way humans orient themselves in any situation. We walked into the deepest emptiness we know, and the first word we reached for was about the loss of company. Not wonder. Not scale. Not the strangeness of a galaxy that had never been disturbed. The loss of company. That instinct is itself a kind of data about what the human animal is made of, about which absences we register most quickly, about the vocabulary our inner life most readily supplies. The void doesn't need us to find it lonely to be what it is. It was what it is long before any word existed for it. The isolation of the galaxies inside it is a physical fact, as solid as any other fact in this story, and it neither improves nor worsens with the word we choose to hang on it. But the choice of word matters for what we understand, for whether we understand the void as a place of loss or a place of unusual stillness, a region of tragedy or a region of different terms. The galaxy in the void is not missing something it once had. It's what the universe makes when a seed lands in emptiness and grows there without the company of others into exactly what its own physics always said it would become. Whether we call that lonely or call it simply itself is a choice about which story we're in, and the science gives us the tools to tell the better one. So what, then, is the shape of the emptiness that holds it, and what keeps the void in the form we find it in? Left alone, an empty region should fill in. Gravity doesn't care about hollowness the way we do. It doesn't preserve openings or protect clearings. It gathers, and it gathers without preference for the shape of what it makes. If you had a void and shut off the universe around it, stopping the expansion, making everything else hold still, the few galaxies at the void's edge would feel the gravity of the surrounding walls more than anything in the center, and they would drift inward, and the void would shrink. The empty region wouldn't hold its shape. It would close. That it doesn't close, that the great hollows maintain their depth and their breadth over billions of years, means something is actively running against the tendency of gravity to fill them. Not a force protecting the void from the outside. Something built into the physics of what a void is that works from the inside out. Think of a watershed, the way a river valley maintains its depth, not because anything digs it or defends it, but because the whole surrounding landscape is arranged so that everything drains into the channels and away from the high ground. The valley isn't held open by a wall. It's held open by the flow itself, by the fact that water moves downhill and the valley is downhill. The valley maintains its own shape by being the place that everything continuously empties toward and through. Nothing protects it. The physics of flow maintains it. The void works by the same principle, run in reverse. It is not the low point that matter drains into. It is the high point on the gravitational landscape, the slight rise that matter rolls away from. Every bit of matter in the void's interior sits on a gentle slope that tips outward toward the denser walls, and over time, everything slides. The interior doesn't stay empty because it's protected. It stays empty because nothing that enters it can stay. The outflow maintains it the way the drainage maintains a valley, not by defending the shape but by continuously removing whatever would fill it. And the outflow doesn't need any special mechanism to keep running. The void empties itself. The less matter it contains, the weaker its central gravity, the steeper the effective slope toward the denser walls, the faster things drift outward. Emptiness produces the conditions for its own maintenance by producing the conditions for its own deepening. This is the same feedback we traced in the runaway, except now it applies not just to the original growth of the void, but to its ongoing existence. The void that is already formed maintains its form by the same logic that formed it. What makes the walls work as walls is the mass that piled up on the void's boundary, enough to create a real gravitational lip, a region dense enough that matter arriving from the void's interior tends to stay, drawn more strongly by the wall's own gravity than by whatever gradient might pull it back in. The wall keeps itself together while the center keeps itself empty. Neither side is passive. The wall is gravitationally active, pulling the last threads of the relic seam toward it, holding what it has, while the center is dynamically active, pushing outward through differential expansion, clearing itself as fast as anything drifts back. The boundary between them isn't a surface. It's a competition that the interior is winning, slowly, by the rules of physics that have always favored the growth of difference. The tendency of a system to maintain a state doesn't require the state to be protected. It only requires that the physics of the situation continuously recreates the conditions for that state. The void doesn't need anything holding it open. It needs only that matter continues to obey gravity, that expansion continues to run faster in underdense regions, and that the difference between the interior and the wall continues to grow. These are not special conditions. They're the ordinary rules. The void persists because the ordinary rules, applied to the particular configuration it achieved, keep recreating it. The void isn't an absence that something failed to fill. It's an active physical state, one that participates in its own maintenance, one that generates the conditions for its own continuation, one that shapes the matter around it while being shaped by it. Calling it empty space, or a gap, or a hole makes it sound inert, like a region where the universe simply forgot to put anything. The void didn't get forgotten. The void is what the universe makes when a particular set of initial conditions and physical rules run together for a sufficient length of time. It's an outcome, not an oversight. And it maintains itself with the same purposeless precision that everything in physics maintains itself, by being the natural consequence of the conditions that gave rise to it. The nothing that holds the shape is, in the end, the very physics of the place. The emptiness is structurally self-reinforcing. The particular configuration of matter and expansion and gravitational gradient that makes a void is a configuration that, once reached, the ordinary rules of physics tend to maintain. There is no active keeping. The void doesn't hold its shape because anything is holding it. It holds its shape because the shape is what the physics keeps building toward. There is a long journey from the interior of the Boötes Void to the room where a person is lying still in the dark. But the physics is the same. The matter in that room, in that body, in the atoms that carry the breath and the warmth and the slow electrical signals of a mind winding down for the night, is almost entirely empty space held in shape by the same forces, at a different scale, running by the same rules. The void out there and the space in here are not different kinds of thing. They're different amounts of the same thing, organized differently by the same physics, maintained by the same tendency of physical rules to keep building the conditions they produce. So what is the emptiness you're actually made of? And what does it mean that the universe spent 14 billion years arranging it into something that could follow a story about a hole in space and find it worth following? The emptiness you're made of is the same kind of emptiness we've been tracing all night, just organized at a scale so small that 14 billion light-years of void and the space inside a single atom sit on the same continuum of physics. Start with the atom. Every atom has a nucleus at its center, a dense knot of protons and neutrons held together by forces so strong they make gravity look like an afterthought. And around that nucleus, a set of electrons that don't orbit like planets in fixed paths, but exist as probability distributions, clouds of where the electron might be spread across a volume that is vast compared to the nucleus at its heart. If you scaled a hydrogen atom up until its nucleus was the size of a marble, the electron's probability cloud would reach out to something like a mile in every direction. Between the marble and the edge of that mile, there is nothing but the mathematics of quantum mechanics describing where the electron is likely to be found. No solid, no stuff. A marble in a mile of mathematical possibility. The body lying in the dark is made almost entirely of that. Not of solid matter, but of nuclei so small they are incomprehensible even to imagination, separated by a scale of empty space that dwarfs them the way the Boötes Void dwarfs the galaxies inside it. The forces holding those atoms in configuration aren't physical objects either. They're fields, interactions, the same kind of purposeless mathematical rules maintaining the conditions that maintain the structure. The same principle we found in the void, running at a scale roughly 40 orders of magnitude smaller. The void out there and the space in here are the same universe, describing itself in different proportions. And the atoms themselves didn't start here. The hydrogen in the body is as old as the universe, formed in the first few minutes, one of the lightest products of the earliest heat. But the carbon and the oxygen and the nitrogen and the calcium and the iron and the sulfur and the phosphorus, all the heavier elements that the body requires to be a body, those came from somewhere else. They were forged in stellar interiors over billions of years, built up through nuclear fusion in cores far hotter than anything on the surface of the sun, and then scattered into space when those stars died, whether in long, quiet exhalations or sudden, violent collapses. The heavy atoms in a human body have passed through at least one star before reaching here. Most of them have passed through more than one. They carry in their nuclei the record of stellar interiors that no longer exist. This is not a metaphor for being connected to the cosmos. It's a literal description of what the body is made of and where it came from. The calcium in the bones was in a stellar core. The iron in the blood was, very likely, formed in a supernova, a star so massive it ended in an explosion that seeded the surrounding space with the elements it had built over millions of years. The body is a temporary configuration of atoms with a very long history, most of which was spent inside other stars or drifting through interstellar space, waiting to be gathered up again. The 14 billion years of cosmic history we trace tonight isn't a backdrop to the listener lying here. It's the manufacturing history of the listener's own material. That material is being maintained right now by the same kind of physics that maintains the void, just at a different scale. The forces that hold the atoms of the body in their configurations are continuously recreating the conditions that maintain those configurations. There is no moment of completion, no final assembled state that simply persists. The body is a process, like the void, a dynamic equilibrium maintained by the continuous operation of physical rules held in shape, not by something static, but by the ongoing tendency of physics to recreate what it has built. The breath that is slowing now, the warmth that is settling, the mind that is releasing its hold on the details of the day, all of it is physics, maintaining a configuration, a particular arrangement of atoms with a particular history, persisting in the way that physics persists its configurations until it doesn't. The void and the body share this too. Neither is permanent. The void will eventually dissolve into something else, as the universe continues its long transformation, its walls dispersed, its interior stretched further by the same expansion that has been running since the beginning. The body, on a shorter timeline, will also disperse, its atoms return to the field they came from, available again for other configurations. What exists now, in both cases, is the temporary form. The form is real. The physics maintaining it is real. But the form is not the final word on what the matter is, only what it's doing right now. Right now, in the dark, that particular configuration of atoms is at rest. The electrical activity in the mind is settling toward the slower patterns of sleep. The muscles are releasing the tensions of the day. The breath is longer and lower. The story has reached the place where stories of this kind are meant to arrive, not at a conclusion about the universe, but at a quiet, which is the thing the universe is mostly made of and the thing the body is asking for. The Boötes Void will be there in the morning, unchanged in any way that matters on the scale of a night's sleep. The cosmic web will still be threading its filaments through the dark. The few galaxies inside the Great Hollow will still be drifting apart, undisturbed, carrying their clean records of how galaxies grow when nothing interferes. The oldest light will still be crossing the sky, carrying the faint map of everything that was. The physics that maintained all of it through tonight will maintain it through the rest of the night and through all the nights ahead of this one. You don't need to hold any of it. It holds itself by the same rules that hold everything. The nothing you found at the center of the void isn't frightening when you followed it this far. It's the ordinary background of the universe, the condition most of space has always been in, the context from which everything that has ever existed emerged and to which it gradually returns. The void is not what was left when something went wrong. The void is what the universe looks like when you step back far enough to see the shape of it. And the shape, it turns out, is mostly open. Thank you for spending this much of the night here, in the dark, following the emptiest place we know, all the way from a mistaken photograph to the atoms in your own hands. It was a long way to travel for something that is, in the end, mostly nothing. I hope the nothing settles you. Sleep well.